Welcome to our channel. In November 1969, something happened on the moon that still sparks debate more than 50 years later. During the Apollo 12 mission, NASA astronauts deliberately crashed the lunar module ascent stage into the moon's surface after returning to the command module. When it hit, seismometers left on the surface recorded something no one expected. The moon rang, not literally like a bell with sound waves you could hear through the vacuum of space, but the seismic reverberations were unmistakable. According to the seismograph data, the moon vibrated for more than 55 minutes. The phrase NASA engineers used to describe it, "The moon rang like a bell." That one sentence launched decades of speculation, research, and even conspiracy theories. Wait, what does it mean for the moon to ring? To understand why this was so bizarre, you have to know what usually happens during a seismic event. On Earth, when an earthquake hits, vibrations move through various layers of rock and magma. Depending on the internal structure crust, mantle, outer, and inner core, those waves speed up, slow down, get absorbed, or change direction. Typically, the Earth dampens the seismic waves quickly, thanks to its molten, dynamic interior. But on the moon, something very different happened. The vibrations didn't dampen quickly at all. Instead, they persisted. They echoed through the body of the moon for nearly an hour, and in a very uniform way. That kind of reverberation suggested something unusual about the moon's interior. It didn't behave like a geologically active body. It behaved more like a giant solid rock, or even something hollow. Hollow moon theories, and why NASA took them seriously. Briefly, the phrase, "the moon is hollow," might sound like a sci-fi fantasy. And to be clear, no credible scientific model supports a truly hollow moon. But at the time, even NASA had to consider the possibility of unusual internal structures. Some early moon models had suggested the moon might have a small or partially molten core. Others assumed it was fully solidified, but the bell-like ringing seemed to indicate a lack of internal damping. No molten core to absorb energy, and a crust that was somehow incredibly rigid and dry. In fact, Apollo seismic experiments across several missions consistently found that moonquakes behave very differently from earthquakes. They last longer, they propagate farther, and they often don't originate in the same types of fault zones we see on Earth. Could the moon be a hollow shell? Probably not. But the way it behaved forced scientists to rethink everything they thought they knew about its internal structure. The seismic data was repeated and got stranger. Apollo 13 never landed on the moon, but it added one of the most important data points to this mystery. In April 1970, the Saturn IVB upper stage, an empty rocket booster, was intentionally crashed into the lunar surface. It impacted with the force of 11 tons of TNT, and the moon's seismometers captured the effects. This time, the moon rang for over 3 hours. Think about that. 3 full hours of measurable vibrations. Some frequencies continued for more than 8 hours. The waves didn't just echo. They built up, then gradually faded in a way that scientists hadn't anticipated. It was like striking a giant crystal-clean, sharp resonance instead of chaotic fracturing. Geophysicist Dr. Clive R. Neal later said, "The moon was ringing like a bell." The implications were deep and not easily explained. So, what's really inside the moon? Let's set aside science fiction and focus on real current science. Modern data, especially from NASA's GRAIL, Gravity Recovery, and Interior Laboratory mission, gives us a much better picture of what's inside the moon. The moon has a thin crust, about 50 kilometers deep on average, a partially molten mantle with different zones of rigidity, a solid inner core and a liquid outer core, but both are much smaller than Earth's. But here's the catch. The moon is extremely dry and low density compared to Earth. That changes how seismic waves travel. Without liquid water and molten rock to absorb and scatter vibrations, seismic waves can bounce around longer and more cleanly, creating that eerie ringing effect. The moon also lacks tectonic plate activity. There's no subduction, no mid-ocean ridges, no frequent crustal movement like on Earth. Instead, its crust is relatively static, cold, dense, and cracked from billions of years of asteroid impacts. So, when energy hits the moon, whether from an impact or a moonquake, it reverberates in a rigid, echo-friendly medium. It's not hollow. It's just dry, brittle, and surprisingly echo-prone. Still, that bell analogy hasn't gone away. Even with updated models, the metaphor has stuck. Some skeptics and fringe theorists have taken the bell-like ringing to mean that the moon is artificial. Theories range from: the moon is a hollow alien base. It was placed there intentionally to watch Earth. It's a giant space station with a crust layered over it. There's no real evidence for any of those ideas. But the Bell moment has become one of those cosmic anomalies that invites storytelling, just like UFOs or the pyramids of Mars. And to be fair, some aspects of the moon's existence are weird, and we'll get to those in future chapters. Its size, orbit, tidal lock, and origin are all strange enough to make you question what's going on up there. The ringing is just the first crack in the surface of what seems like a deeper mystery. Why does it still matter today? You might wonder, why should anyone care that the moon rings? Isn't that just a quirky physics thing? Actually, this phenomenon is a key to understanding planetary formation. The way seismic waves move through a planetary body tells us how it formed, how it evolved, and what lies beneath the surface. Earthquakes taught us about Earth's core. Moonquakes are doing the same for the moon. Understanding the moon's interior helps us know whether it ever had a dynamo, like Earth's magnetic field, model early solar system collisions and accretion processes, plan future lunar bases since quakes affect construction, and determine whether water or minerals lie beneath the crust. Every time we detect a moonquake or impact vibration, we learn more about the moon's hidden structure. And yes, sometimes those lessons sound like bells. So, is the moon still ringing? Not literally, but the mystery hasn't gone away. In fact, as we prepare to return humans to the moon with NASA's Artemis program, scientists are planning new seismic experiments, this time with modern instruments and wider coverage. The moon may hold more secrets beneath its surface. And if it still rings when we crash something into it, that's a sound we'll be listening for again. For something we see almost every night of our lives, the moon is shockingly mysterious. You'd think that by now, scientists would agree on how it formed, but they don't. In fact, the moon's origin is still one of the most debated topics in planetary science. And every time a theory seems to fit, new evidence comes along that tears it apart. The truth is, we don't know exactly where the moon came from. We have guesses, we have models, we have simulations, but each one has major flaws. And the more we learn, the more the mystery deepens. The most popular theory, the one you'll find in textbooks and documentaries, is called the giant impact hypothesis. It says that over 4 billion years ago, a Mars-sized body slammed into the early Earth. This planet-sized projectile, sometimes called Theia, collided with such force that debris was blasted into orbit around Earth. That debris supposedly formed a disk, and over time, it clumped together and became the moon. It's a bold and dramatic story, and for a while, it seemed to explain a lot. The moon's lack of a dense iron core made sense. It would have formed mostly from the outer layers of Earth and Theia, not the iron-rich centers. The moon's relatively small size and its distance from Earth also fit the model, and simulations showed that the physics checked out. A collision like that really could launch enough debris into orbit to form a moon. But there's a problem, actually. When Apollo astronauts brought back samples from the moon, scientists compared their composition to rocks on Earth. And what they found was surprising. They were almost identical. Same isotopes of oxygen, same ratios of key elements, nearly a chemical match. That shouldn't happen. If the moon were partly made from another planet, Theia, its rock should have different fingerprints, different oxygen isotopes at the very least, but we don't see that. It's as if the moon is made from Earth and only Earth. That's the first crack in the giant impact theory. The chemistry doesn't match the story. Some scientists tried to fix the model by tweaking the collision. What if Theia had the exact same isotopic makeup as Earth? What if the collision mixed the two bodies so thoroughly that their differences were erased? What if Earth spun faster than expected and flung out more of itself? These are clever patches, but they raise even more questions. What are the odds that two separate planets formed in different parts of the solar system would have such an eerily identical chemical signature? It's possible, but unlikely. And even if the mixing was that complete, why is the moon's composition still so close to Earth as mantle and not a more random mix? So, some scientists explored other models. One idea is the co-formation theory. It suggests that Earth and the moon formed together from the same disk of material orbiting the sun. They were like twins growing side by side. That would explain the chemical similarity. They'd be made from the same stuff. But this theory runs into trouble with angular momentum. If the Earth and moon formed together, they shouldn't have the orbital relationship they do now. The moon's size, distance, and motion don't line up with what we'd expect from co-formation. The math doesn't hold. Then there's the capture theory. This one says the moon formed elsewhere and was later pulled into Earth's orbit by gravity. That could explain why the moon is such an odd match for other solar system moons. It's much larger relative to its planet than most moons are. Maybe it was wandering the early solar system and got snagged. But again, there are problems. Capturing something as massive as the moon without it crashing into Earth or flying off into space is extremely difficult. Gravity doesn't just politely pick up huge objects and place them in perfect orbits. You'd need a precise set of conditions, a slowing mechanism, a near miss, a transfer of energy. And we don't see signs of that in the Earth-Moon system. It would be like tossing a baseball from a car window and having it fall into a perfect spiral around a lamppost. Not impossible, but not very likely either. Other theories go even further outside the box. Some suggest the moon formed from multiple smaller collisions rather than one big one. Others propose that Earth once had more than one moon, and they merged over time. There are even ideas involving vapor clouds and molten droplets condensing in orbit. But none of these alternatives fully solve the core issues. They all struggle with some combination of physics, chemistry, or timing. They can't quite match the moon we actually see. And then there's the weird stuff, the parts that don't fit neatly into any theory, like the moon's orbital relationship with Earth. It just happens to be at a distance where it appears the same size as the sun in the sky, allowing for perfect total solar eclipses. That's a coincidence so strange, it's been used in everything from mythology to conspiracy theories. Or the fact that the moon is unusually large compared to Earth, way bigger than most moons relative to their planets, or that it always shows the same face to us, locked in synchronous rotation. Some scientists see these as natural results of tidal forces and orbital dynamics. Others think there's something deeper going on. The bottom line is this: we don't know for sure how the moon formed. The giant impact theory is still the best we've got, but it's not airtight. It has serious holes. The chemical match with Earth is too close. The physics are too finely tuned. And the more data we get from lunar rocks, from orbiters, from simulations, the more complex the picture becomes. It's one of those rare scientific problems where the deeper we dig, the less certain we become. The moon is there, hanging silently in the sky, watching us. But its origin story is still missing its final chapter. And that's not just a gap in our understanding. It's a mystery at the heart of everything we know about how planets and moons come to be. Because if we can't explain the moon, then how much do we really know about our own cosmic backyard? It's easy to think of the moon as a permanent fixture in our sky. It's been there every night for all of human history, glowing quietly, setting the rhythm for tides and calendars and myths. But the moon isn't fixed. It isn't even staying still. In fact, it's slowly escaping us. Every year, inch by inch, the moon is drifting farther away from Earth. And while that might sound like no big deal, it's having strange and measurable effects on something you might not expect: time itself. This isn't some poetic idea about the moon changing our perception of time. It's literal. The moon is altering the length of Earth's day, making it longer, very slowly, but relentlessly. Right now, the moon is receding at about 3.8 centimeters per year. That's roughly the same rate your fingernails grow. Doesn't sound like much, but across millions and billions of years, it adds up to something enormous. To understand what's going on, you need to know about tides, not the waves at the beach, but the gravitational dance behind them. The moon's gravity pulls on Earth's oceans, creating tidal bulges. These bulges don't line up perfectly with the moon because Earth is spinning. Instead, they're dragged slightly ahead of the moon in its orbit. That forward-leaning bulge tugs back on the moon, giving it a small but steady boost in energy. And in return, the moon pulls back on Earth, slowing our rotation. This is tidal friction. It's invisible, it's constant, and it's been happening for billions of years. The result is that Earth's rotation is gradually decelerating, which means days are getting longer, not by much. Right now, we're adding about 1.7 milliseconds every century. But in the distant past, Earth spun much faster. Hundreds of millions of years ago, a day was just 22 hours long. Go back even further, say 1.4 billion years, and a day was only about 18 hours. The moon was closer back then, to about 341,000 kilometers away, instead of the 384,400 kilometers it averages today. You would have seen a moon significantly larger in the sky. And the tides? They would have been stronger, more dramatic, crashing across coastlines with incredible force. Today, laser reflectors left on the moon by Apollo astronauts allow us to measure the moon's distance with centimeter precision. By bouncing lasers off these mirrors and measuring the return time, scientists have confirmed that the moon is drifting away, and Earth's rotation is slowing exactly as predicted by tidal theory. This connection between the moon and the length of our day is one of the most subtle yet powerful interactions in the solar system. It means the moon is not just a passive object orbiting Earth. It's actively reshaping how time flows on our planet. But this isn't just a past or present phenomenon. It also affects the future. If nothing else changes, no external forces, no massive events, then in the very distant future, the Earth and moon will become tidally locked to each other. That means one side of Earth would always face the moon, just as one side of the moon already always faces Earth. Days on Earth would eventually stretch to match the moon's orbital period, about 47 days long, and time would feel completely different. No sunrise and sunset every 24 hours. No typical daylight cycle. Life would look nothing like it does now. Of course, this won't happen for billions of years, and something else will almost certainly interfere first, like the sun expanding into a red giant and engulfing both Earth and the moon. But the point remains. The system is evolving. The moon is changing the rhythm of Earth ever so slowly, but with monumental consequences over geological time. There's also another strange twist. Some scientists believe the moon's recession may not have always been this smooth. There are periods in Earth's past, based on rock layers and fossil records, where tidal patterns seem to shift more rapidly than they should. One possibility is that the moon's rate of movement isn't constant over time. Changes in ocean configuration, continental drift, and even glaciation cycles may influence how tidal energy is transferred. In other words, Earth's geography could be affecting how quickly the moon drifts away. It's not just a one-way system. It's a complex feedback loop connecting land, sea, sky, and time itself. The moon's recession also plays into orbital mechanics and climate. Without the moon's stabilizing gravitational pull, Earth's axial tilt might vary wildly. Right now, our tilt stays within a fairly narrow range, which keeps our seasons stable. But if the moon were to continue drifting away or disappear entirely, that tilt could wobble chaotically. Some models suggest it could swing from nearly 0 to over 60. That kind of instability would have devastating effects on global climate, ecosystems, and the conditions needed for life. And here, as the eerie part, we owe our current version of time to this exact delicate system. The fact that we have 24-hour days and predictable seasons isn't just luck. It's the result of an ongoing gravitational relationship that began 4.5 billion years ago and is still unfolding. The moon has been our silent timekeeper since long before humans evolved. Without it, the very concept of a day as we know it would be unrecognizable. So next time you look up at the moon, remember it's leaving slowly, steadily, invisibly. And as it does, it's stretching out our days, 1 millisecond at a time. Over generations, that change is imperceptible. But over eons, it's rewriting the history of time on Earth. The moon is drifting, time is bending, and nothing, not even the length of a day, is as permanent as it seems. There's something eerie about looking up at the moon during a solar eclipse. For a few brief minutes, it fits perfectly over the sun, not too big, not too small. Just the right size to cover the sun's disk while leaving the glowing corona visible. It's one of the most breathtaking sights in nature. But here's the strange part. That perfect fit is a fluke, a cosmic coincidence. Or at least, that's what we've always been told. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. That ratio means the two objects appear almost exactly the same size in our sky, around half a degree wide. That's why we get perfect total solar eclipses. If the moon was slightly smaller, we'd only get annular eclipses, a ring of fire with the sun still peeking out. If it were larger or closer, the sun would vanish completely. But right now, it's just right. The moon and sun line up so precisely that the lunar disk slips over the solar surface with the precision of a lens cap clicking into place. It's the kind of alignment that feels engineered, too exact to be random. And yet, according to mainstream astronomy, it is random, a pure coincidence born from the chaotic evolution of orbital mechanics. No plan, no design, just math. But the more you look at the numbers, the weirder it gets. The moon's diameter is about 3,474 kilometers. The sun is about 1.39 million kilometers. Divide one by the other, and you get roughly 400. The moon's average distance from Earth is about 384,400 kilometers. The sun's average distance is about 149.6 million kilometers. Again, divide one by the other, and you get roughly 400. It's not exact, these values vary slightly due to elliptical orbits, but the match is close enough to produce total eclipses that are almost unnervingly perfect. What are the odds of that happening? Not just having a large moon, but having one that produces the only known total eclipses like this in our entire solar system. Earth is the only planet that experiences them. Other moons exist, some are bigger, some are closer to their planets, but none create eclipses like ours. Mars has 2 tiny potato-shaped moons that can't even come close. Jupiter's massive moons never align with the sun the way ours does. It's a unique phenomenon, and it just happens to occur on the one planet known to support life. Some see that as a coincidence. Others see it as something more, a clue, maybe even a signature. In fact, this alignment has been a magnet for speculation for centuries. Ancient cultures saw eclipses as omens, celestial battles, or messages from the gods. Today, some theorists still wonder, Is it all just math, or is there a deeper pattern here that we don't understand yet? There's even more to the puzzle. The moon's orbit isn't static. It's changing. As we saw earlier, the moon is moving away from Earth by about 3.8 centimeters per year. That means millions of years ago, it was closer, and it would have looked larger in the sky. Back then, eclipses would have been longer and more complete. And millions of years from now, the moon will be farther away and too small to fully cover the sun. Total eclipses will stop happening altogether. We're living in a brief window of time where this perfect alignment is even possible. Think about that. Out of the billions of years Earth has existed and the billions of years to come, we just happen to be alive during the relatively short period when the moon perfectly matches the sun in apparent size. That's not just rare. It's razor thin in terms of timing. We're in a cosmic moment that will come and go like a spark. There are other odd numerical relationships too. The moon spins on its axis once every 27.3 days. It also orbits Earth once every 27.3 days. That's why we always see the same face. The moon is tidally locked. But here's the twist. The moon's orbit isn't circular. It's elliptical. So, its distance from Earth varies. It's sometimes closer, perigee, and sometimes farther, apogee. That means the moon sometimes appears slightly larger or smaller in the sky, which is why we get different kinds of eclipses. And even those variations follow predictable mathematical cycles. The Saros cycle, for example, is an eclipse pattern that lasts about 18 years, 11 days, and 8 hours. After each Saros cycle, the Earth, Moon, and Sun return to roughly the same geometry, and nearly identical eclipses repeat. These patterns were known to ancient Babylonian astronomers thousands of years ago, long before modern science could explain them. They charted the heavens and discovered a mathematical order in something that looked chaotic. And we're still discovering new layers of that order today. Of course, science doesn't assign meaning to coincidences. It explains them. Orbital mechanics can model the moon's distance, velocity, and rotation. We can calculate how its position evolved from its formation and how it will continue to change. But math doesn't answer the deeper questions, the why behind the what. Why do we live at the precise moment when the moon creates perfect eclipses? Why does this celestial object, unique in all the solar system, appear perfectly matched to the sun from our perspective? Some scientists dismiss these questions as anthropic accidents. We notice them because we re-ear to notice them. Others wonder if these alignments hint at unknown laws or deeper cosmic principles we haven't discovered yet. And a few, from the fringes of science, suggest even more outlandish possibilities. That the moon was placed, not born. That its orbit isn't just the result of physics, but intent. These ideas aren't supported by mainstream science, but they continue to capture people's imaginations, partly because the math feels so deliberate. Even without venturing into the speculative, the fact remains, the moon is uniquely positioned to produce one of nature's most dramatic and inspiring spectacles. Its size and distance line up with uncanny precision to give us perfect solar eclipses events that have shaped history, inspired fear, driven science, and brought millions of people to a standstill in the middle of the day. And it won't last. Every eclipse you see is part of a countdown. Eventually, total eclipses will fade into the past, leaving only memories and photographs. Future civilizations, millions of years from now, will never know what it was like to stand in the shadow of a moon that fit the sun like a puzzle piece. They'll look up and see something smaller, dimmer, less perfect. So the next time the sky goes dark and the stars come out at midday, remember you're watching a mathematical miracle, one that's timed almost too perfectly. The moon and sun align not because they have to, but because somehow they do. Whether it's coincidence, design, or something in between, the result is the same. A cosmic alignment that continues to make us wonder if there is more to the moon than we've ever imagined. It sounds impossible, even backward. How can something orbiting Earth be older than Earth itself? After all, the moon is supposed to be a child of Earth, born from the same ancient dust cloud or carved off in a collision. But the moon holds secrets buried in its crust, and some of them have forced scientists to question everything they thought they knew about when and how our nearest neighbor was formed. The truth is, certain parts of the moon appear to be not just ancient, but pre-Earth ancient, older than our planet, and that shouldn't be possible. When Apollo astronauts brought back lunar samples in the late 1960s and early 70s, scientists expected to find rocks similar in age to Earth, maybe a little younger, depending on which moon formation theory was correct. Instead, what they found were anorthosids, bright reflective rocks that make up the highlands of the moon. These rocks were old, incredibly old. Radiometric dating showed some of them were 4.46 billion years old, just a few tens of millions of years younger than the estimated age of the solar system itself. That number is stunning. It suggests these rocks formed when the solar system was still a turbulent disk of dust, gas, and colliding planetesimals. Now, here's the kicker. Earth's oldest known rocks are significantly younger. The oldest confirmed terrestrial rocks are around 4.03 billion years old. That's a gap of over 400 million years. Million. It's not because Earth wasn't here yet. It's because Earth is geologically active. Plate tectonics, erosion, and volcanic recycling constantly reshape and erase its surface. But the moon has no such mechanism. No atmosphere, no erosion, no shifting continents. Which means when something forms on the moon and survives an impact, it can stay exactly where it is for billions of years, a frozen time capsule from the dawn of the solar system. And yet, even with that preservation in mind, there's a twist. Some lunar zircons, microscopic crystals found in Apollo samples and meteorites that originated from the moon, have been dated to 4.51 billion years ago. That's before Earth's crust even solidified. Some of these crystals may have even predated the moon's formation, existing as fragments from other planetary bodies that were incorporated into the moon during its creation. If that's true, then these pieces of the moon are not just older than Earth's surface. They may be older than Earth, period. This has reopened long-standing debates about the moon's origin. The most accepted model, the giant impact hypothesis, assumes that a Mars-sized planet collided with the early Earth around 4.5 billion years ago, and the moon formed from the resulting debris. But if parts of the moon are older than Earth's crust, that raises questions. Did those materials survive the colossal impact somehow? Did they come from the impactor, the hypothetical planet Theia, and not Earth at all? And if so, what does that make the moon? A mix of two worlds, a splinter of a lost planet, a cosmic archive of places that no longer exist? There's also the possibility that the moon wasn't formed entirely from scratch during the impact. Some newer models suggest that, rather than a total destruction and rebuild event, the moon might have formed from pieces of already differentiated bodies. That means the materials, the rocks, the minerals, the crystals had histories that long predated their assembly into the moon as we know it. So, when we say parts of the moon are older than Earth, we're not just talking about age. We're talking about inheritance. The moon might be made of recycled planetary history pieces from multiple worlds that collided, shattered, and reassembled in deep time. And then there's the even stranger idea that the moon may have formed earlier than Earth itself. It's not a widely accepted theory, but a few models suggest that if Theia was a fully formed planetary embryo, and if it formed closer to the Sun, it may have cooled and developed a crust earlier than Proto-Earth did. In that scenario, when the two planets collided, the moon would retain material from the older, more evolved body. That would make the moon, in a very real sense, the older sibling in this gravitational partnership. Another intriguing detail is where these ancient lunar rocks are found. Most of them come from the moon's highlands, bright cratered regions that stand in contrast to the darker Maria or lunar seas. The highlands are thought to be remnants of the moon's original crust, formed when a global magma ocean slowly cooled and crystallized. That's right. At one point, the entire moon may have been a molten ball of lava, glowing in the night like a newborn star. As it cooled, lighter minerals floated to the surface, forming the highlands. These were the first true rocks of the moon, and some of them are the very ones we're still studying today. These ancient rocks aren't just old, they're chemically distinct. They lack water-bearing minerals. They show signs of formation in a vacuum, under extreme heat, with no atmosphere to protect them. They tell us what it was like to be a planetesimal in the early solar system, constantly bombarded, rapidly heated, violently reshaped. Every crater, every fracture in these rocks holds a clue to the solar system's most chaotic era. Earth's early history has been mostly erased by geology, but the moon remembers. The moon has kept the record intact. Even the moon as meteorites, rocks blasted off its surface by impacts and later found on Earth, tell the same story. Some of them contain clasts that are shock-melted and heavily altered, hinting at collisions that occurred long before the Earth-Moon system stabilized. These aren't just rocks. They're survivors, fossils from before the world as we know it even existed. It's a strange realization that our moon, which has always felt like a companion, a satellite, a child of Earth, might actually be holding the oldest pieces of the solar system in its crust. That it might be the best archive we have of a time before Earth's oceans, before its continents, before even its stable surface. We walked on it, left our footprints, and planted our flags. But we're only beginning to understand what we are really standing on when we stand on the moon. Because under that gray dust and impact-scarred terrain is a deeper history. A story older than Earth, a record that predates our planet, our biosphere, and everything we call home. And that story is written in rocks that don't lie, rocks that are older than anything we've ever touched. Parts of the moon are older than Earth itself. And the more we study them, the more they remind us that our own planet is just one chapter in a much longer cosmic book. And the moon is holding the preface. This one sounds like science fiction. The moon, that pale, silent sphere drifting through our sky, has a tail, a real physical tail, like a comet streaking through the void. And what's even stranger, that tail actually passes over Earth, not metaphorically, not symbolically, literally. Once a month, Earth moves through a stream of particles drifting off the moon like smoke from an invisible fire. It happens quietly, invisibly, and most people on Earth have no idea it's happening, even though it's been happening forever. The tail isn't made of rock or gas. It's not visible to the naked eye. It's composed mostly of sodium atoms, tiny lightweight particles that are blasted off the moon's surface and sent streaming into space. And yet, despite their size, they travel tens of thousands of kilometers and form a massive, diffuse cloud that trails the moon like an invisible ribbon. This isn't just some poetic idea dreamed up by theorists. It's been observed, detected, measured, and once every month, for a brief period, Earth passes right through it. The discovery of the moon's sodium tail goes back to the late 1990s, when astronomers, using extremely sensitive instruments, began detecting a faint glow of sodium light near the new moon, a glow that should not have been there. Sodium emits a specific wavelength of yellow-orange light when energized, and researchers started noticing that this glow intensified during certain parts of the lunar cycle. When they mapped the data, it showed something unexpected: a huge comet-like tail extending from the moon and sweeping across space in the direction opposite the sun. The process starts with micrometeoroids, tiny bits of space rock that are constantly bombarding the moon. Because the moon has no atmosphere, these impacts hit the surface directly with enormous energy relative to their size. Each impact vaporizes a tiny bit of lunar rock, releasing atoms into space. Among those atoms is sodium, a volatile element that doesn't bond easily with others and can be easily accelerated by solar radiation pressure. That is, light from the sun pushing on the atoms like a gentle but relentless breeze. As solar radiation pushes these sodium atoms away from the moon, they form a long, narrow tail that can stretch for more than 100,000 kilometers. That tail always points away from the sun, just like a comet. And during the new moon phase, when the moon is directly between Earth and the sun, Earth briefly moves through the densest part of the sodium stream. We don't feel it, we don't see it, but our planet gets washed in lunar atoms for several hours every month. This tail is incredibly faint, and it's taken decades of refinement in observation technology to study it properly. Specialized instruments called sodium spectrometers can detect the unique glow of the sodium tail when the moon is new. It appears as a dim, diffuse patch of light, invisible to the human eye, but unmistakable through the right filters. The tail doesn't have any physical effect on Earth. It doesn't influence weather or magnetic fields. It won't make you glow yellow. But its presence is a reminder of something far more profound. The moon is not inert. It's not just sitting there, locked in orbit, doing nothing. It's leaking. It's interacting with space. It's active in ways we're only beginning to understand. And it's not just sodium. Other elements are released from the moon's surface too: potassium, helium, argon. They're part of what's called the lunar exosphere, an extremely thin atmosphere, almost a vacuum, but still technically a layer of gases surrounding the moon. It is nothing like Earth's atmosphere. You couldn't breathe it or even detect it without instruments, but it exists and it's dynamic. In fact, the moon's exosphere changes depending on several factors. Micrometeorite impacts increase during certain times of year, like during the Leonid meteor shower, when Earth passes through a dense stream of comet debris. During those periods, the moon gets pelted even more than usual, and its sodium tail intensifies. More impacts mean more vaporized atoms, which means a bigger, brighter, longer tail. It's like the moon exhales more deeply in response to being struck. Solar activity plays a role too. During periods of intense solar radiation, solar flares, coronal mass ejections, the increased energy can knock more particles loose from the moon's surface. The tail, then, is not just a static feature. It pulses, breathes, responds to the environment around it. It's a subtle, ghostly signature of lunar life, not biological life, but planetary activity shaped by constant bombardment and solar forces. In 2006, NASA's Messenger spacecraft, en route to Mercury, turned its instruments toward the moon and observed the sodium tail extending more than 600,000 kilometers into space. That's more than 1.5 times the distance from the Earth to the moon. Let that sink in. Something is trailing off the moon at a planetary scale, stretching through space so far it rivals the orbits of nearby satellites. And yet, it's so diffuse, so delicate, that we only discovered it in the past few decades. All of this reshapes our picture of the moon. It's not a dead rock. It's a dynamic body, constantly shedding material, constantly interacting with space, constantly whispering across the void with streams of sodium atoms. It's a process we don't see, don't feel, and never notice. But it's happening above our heads every single month. And maybe the strangest part of all is that we're inside it. Earth is part of this monthly rhythm, moving through the ghost trail of lunar atoms. Our planet, so big, so grounded, gets brushed by the faintest exhale of the moon, like a silent breeze from a place we thought was silent. The moon has a tail, and once a month, it sweeps over Earth without a sound, a reminder that the moon is far more alive, far more strange, and far more connected to us than we've ever truly realized. We tend to think of the moon as silent, frozen, and immobile, a place untouched by weather, tectonics, or any kind of surface drama. After all, it's been the same for billions of years, right? Craters don't change. Dust doesn't shift. It's so stable, we use it to calibrate instruments and as a base for telescopic imaging. But underneath that calm, ancient surface, the moon is not as still as it seems. Because the moon has quakes, and some of them are powerful enough to threaten future human bases. They're called moonquakes, and they're very real. Apollo astronauts didn't just go to the moon to plant flags and collect rocks. They also installed instruments, including seismometers, to listen for vibrations deep inside the lunar body. What those instruments recorded changed our understanding of the moon's geology forever. Over the course of several years, they picked up thousands of quakes, and some of them were not just little rumbles. A few were massive, lasting for minutes and carrying energy across huge distances. Unlike earthquakes, which often occur along fault lines or subduction zones, moonquakes are a different beast. Scientists have identified 4 types, each with its own cause and behavior. The first are deep moonquakes, which occur around 700 to 1,200 kilometers beneath the surface. These are regular and seem to be tied to tidal forces caused by the gravitational pull between Earth and the moon. As the Earth tugs on the moon, the stress builds up and releases in these rhythmic, deep, internal events. Then there are shallow moonquakes, which are more concerning and much more mysterious. These occur just tens of kilometers beneath the surface, and some have reached magnitudes of 5.5 on the Richter scale. That might not sound massive compared to Earth's biggest quakes, but on the moon, with its dry, rigid crust, the effects can be much more intense. A quake of that magnitude on the moon could rattle a structure for tens of minutes, with no natural damping from soil, water, or atmosphere to soften the motion. If we were to build habitats or research stations on the lunar surface, especially permanent ones, these quakes could shake them with surprising force, and they're not rare. Between 1969 and 1977, the Apollo seismic network recorded 28 shallow moonquakes, strong enough to be detected across long distances. Some of them lasted over 10 minutes. That duration is a big deal. On Earth, seismic waves usually fade after a few seconds or minutes, absorbed by water or molten rock. But the moon is dry and brittle. Once the energy starts moving, it bounces around inside like a bell, taking forever to die out. You don't just get one tremor. You get an extended, vibrating session of seismic turbulence. Then there are thermal moonquakes, which occur when the surface temperature shifts dramatically. The moon has no atmosphere, so during the day, temperatures climb to about 127 degrees Celsius, 260 degrees Fahrenheit, and at night, they plunge to minus 173 degrees Celsius, minus 280 degrees Fahrenheit. That's a swing of over 300 degrees Celsius every single lunar day. As the sun rises and heats the surface, the rock expands. That expansion can create cracks, fractures, and yes, small quakes. You won't feel these if you're walking around in a spacesuit, but they're always happening, clicking and popping as the crust adjusts to the brutal temperature changes. It's like the entire surface is settling, creaking under the weight of ancient thermal fatigue. The last type are impact-induced moonquakes caused by meteoroids slamming into the surface. These are rare but dramatic. The moon's lack of atmosphere means space rocks don't burn up before impact. They hit hard, fast, and direct. A large enough impact can send seismic waves rippling through the moon, triggering quakes in distant regions. One big enough or close enough could compromise structures, especially if they're built in poorly reinforced terrain. This all presents a major challenge for future lunar missions. NASA's Artemis program, China's Change series, and commercial partners like SpaceX and Blue Origin are all planning to put long-term habitats on the moon. That means not just surviving the landing, but surviving the moon itself. Engineers now have to design buildings that can withstand long-duration seismic shaking on a surface where the ground might vibrate like a tuning fork. Structures need to absorb energy without collapsing. Foundations need to hold on loose, dusty regolith, and equipment must be protected from sudden jolts that could tear cables, tip modules, or knock over scientific instruments. And because shallow moonquakes can happen without warning, it's not a matter of if, but when. Unlike Earth, the Moon doesn't have global monitoring systems or a seismological warning network. There are no satellites tracking tectonic pressure. The best we can do is study the old Apollo data and guess where quakes might happen next. Future missions will need to bring updated seismic sensors, modern, sensitive, networked to rebuild that warning system and maybe even learn how to predict moonquakes before they happen. One particularly troubling factor is that many of the recorded shallow moonquakes occurred near regions being considered for future bases, such as the lunar South Pole, where water ice may be hidden in permanently shadowed craters. These regions are attractive for exploration, but if they're seismically active, they could pose a significant risk to long-term occupation. Some scientists believe these quakes are remnants of an ancient, still cooling interior echoes of the Moon's violent past, shaking out the last bits of thermal energy from its formation. Others think they may be part of ongoing geological activity, slow and subtle, but persistent. The Moon is not dead. It's sleeping, and every now and then, it stirs. In 2019, researchers revisiting Apollo seismic data noticed something else strange. One shallow moonquake appeared to coincide almost perfectly with the location of a newly discovered fault line. A ridge on the Moon's surface that seems to have formed from crustal compression. In other words, the Moon's surface might still be shifting, albeit very slowly. It could still be cracking under its own weight, reshaping itself and releasing seismic energy in the process. If that's true, then we're not just building bases on a quiet relic. We're building them on a living, shifting crust that no one fully understands yet. So yes, the Moon has quakes, and some of them are strong enough to rattle instruments, strong enough to damage, structures strong enough to remind us that even the most ancient cratered and airless bodies can still surprise us with motion from deep within. The next time you look up at the Moon and see its silent face staring down, remember that deep below that calm surface, something is still moving slowly, quietly, and sometimes with enough force to shake the stars. It is one of the most persistent myths in astronomy. The phrase, the dark side of the Moon. You've heard it in songs, movies, even casual conversation. It conjures images of a cold, pitch-black lunar hemisphere, shrouded in mystery, hidden from sight and sunlight alike. People talk about it as if it's a shadow realm, a place untouched by light or knowledge. But here is the truth. The so-called dark side of the Moon isn't actually dark at all. In fact, it gets just as much sunlight as the side we see from Earth. What it really is hidden. To understand why this idea exists and why it's so wrong, we need to talk about how the Moon moves. The Moon is tidally locked to Earth. That means it rotates on its axis at the exact same rate that it orbits our planet, about once every 27.3 days. Because of that synchronicity, the same side of the Moon always faces Earth. We see one hemisphere, and only one, over and over again. The other side, what people call the dark side, is never visible from Earth without the help of spacecraft. But light doesn't care what direction you're looking from. The far side of the Moon, the so-called dark side, gets just as much sunlight as the near side. It experiences lunar day and night, just like the part we see. Half the time, it's fully lit. The other half, it's in shadow, just like Earth, just like every other rotating body in the solar system. There's no permanent darkness, no cosmic shadow. The only thing dark about it is our perspective. So where did the term come from? Mostly from misunderstanding. Before spaceflight, no one had ever seen the far side of the Moon. It was a mystery invisible from Earth, unreachable by telescope. And when something is invisible, we tend to imagine it as shadowy, foreboding, even sinister. The phrase dark side became a poetic stand-in for unknown side, but it's not technically accurate, not even close. The far side of the moon was finally revealed in 1959 when the Soviet spacecraft Luna 3 took the first grainy photographs of it. What they showed surprised everyone. The far side looks dramatically different from the side we're used to. It's more cratered, rougher, with almost none of the smooth, dark plains or maria that dominate the near side. Those dark areas we see from Earth are actually ancient lava flows, basaltic plains formed by volcanic activity billions of years ago. The far side? It barely has any, just a few small patches. The rest is a jagged, pockmarked landscape of highlands and impact scars. Why the difference? That's a mystery scientists are still trying to fully explain. One theory suggests the crust on the far side is thicker, making it harder for magma to rise and spread. Another suggests that early Earth might have influenced the moon's heat distribution when they were both still molten, effectively cooking one side more than the other. The result is a two-faced moon, sculpted by ancient forces we're only beginning to understand. And here's another twist. The far side isn't completely hidden anymore. We've mapped it in incredible detail. NASA's Lunar Reconnaissance Orbiter, China's Change missions, and other spacecraft have taken high-resolution images of every crater, ridge, and plain. The dark side is now one of the most studied places in the solar system. We know its topography better than parts of Earth's ocean floor. In fact, the far side is so well mapped and so unique that it has become a target for future missions. In 2019, China's Chang'e 4 made history by landing the first spacecraft and rover on the far side of the moon, in the Von Karman crater. That's something no one had ever done before. The far side poses communication challenges because it's blocked from direct radio contact with Earth. But China solved that by placing a relay satellite called Kuiqiao in lunar orbit, allowing them to talk to the lander from the other side of the moon. That mission marked a turning point, not just in lunar exploration, but in the way we think about the far side altogether. It's not dark, it's not unreachable, it's just hidden. And now, even that's changing. But the mythology of the dark side persists, probably because there's something deeply human about the concept. We're drawn to unseen places. We imagine they hold secrets, dangers, truths that daylight can't reveal. And for most of human history, the moon's far side was the ultimate unseen place, a hemisphere of mystery, orbiting silently above us, never turning, never winking. It became a canvas for imagination. Aliens, bases, conspiracies, all of it hiding on the dark side, just out of view. Science has stripped that mystery away, but in doing so, it's given us something even more fascinating. A real place with real terrain and real history, one that doesn't need to be cloaked in shadow to be awe-inspiring. The far side of the moon is battered, ancient, and otherworldly. It holds some of the oldest and most pristine craters in the solar system. It may even hold clues to what the moon looked like before Earth had oceans. One day, it might host telescopes shielded from Earth's radio noise, or science bases buried beneath the regolith. It might even be the first place humans settle on the moon's surface, out of sight, out of radio range, what we used to call the dark side. So, let's retire the myth. The far side of the moon isn't dark. It's not evil. It's not hiding in the shadows. It's just hidden by gravity, by orbital mechanics, by the fact that the moon and Earth are locked in an eternal gravitational embrace. One face always turned toward us, the other gazing silently out into deep space. And thanks to modern science, we're no longer blind to that hidden face. We've seen it, mapped it, landed on it, and in doing so, we've transformed the dark side from a mystery into a frontier. Rust is a product of Earth, or at least, that's what we used to think. It's what happens when iron meets water and oxygen, a chemical reaction that turns metal red and flaky. We see it in old bridges, abandoned cars, corroded tools. So, it makes sense to assume that rust couldn't possibly exist on the moon. After all, the moon has no atmosphere, no oxygen, no liquid water. It's dry, dead, and airless. And yet, somehow, scientists have found actual rust on the moon, and no one expected it. The discovery came in 2020 when researchers analyzing data from India's Chandrayaan-1 lunar orbiter noticed something strange. This spacecraft had been using a NASA-built instrument called the Moon Mineralogy Mapper, or M3, to study the moon's surface composition. Most of what it found was expected: silicates, pyroxenes, olivines, and iron-bearing minerals. But then, the data flagged something odd: spectral signatures that looked like hematite. Hematite is a form of iron oxide, a type of rust, not just iron, but iron oxidized, meaning it's been exposed to oxygen and moisture. That raised a huge red flag. How could there be hematite on the moon? It's supposed to be impossible. You need the right ingredients, and the moon is missing all of them. No liquid water, no breathable air, just a vacuum, some solar wind, and a lot of dry rock. So at first, scientists thought the data might be wrong, a glitch, a misreading. But then they cross-checked it. They looked at other lunar regions, other angles, and other lighting conditions. The hematite signature kept showing up, mostly at higher lunar latitudes near the poles, especially on the far side of the moon. Not everywhere, but enough to matter. This wasn't a one-off fluke. Something was rusting iron on the moon. That left researchers with a question that has no easy answer. How? One theory involves a surprising culprit: Earth's atmosphere. It turns out that Earth's magnetic field extends far beyond our planet. During the moon's orbit, especially when it passes through the region known as the magnetotail, the moon gets temporarily shielded from the solar wind. And at the same time, it's briefly bathed in a thin stream of oxygen atoms leaking from Earth's upper atmosphere. This tail of atmospheric escape stretches far into space, and once a month, the moon sweeps through it like a brushstroke. In those moments, there's a supply of oxygen, not a lot, but maybe just enough. And if iron-bearing minerals on the moon are exposed to that oxygen, especially in regions where frost or trace water molecules exist in the regolith, and under the right conditions, rust might form slowly over millions of years on a planet where nothing should rust at all. Adding to the mystery, we now know that water molecules do exist on the moon. Not pools, not lakes, not even ice cubes, but tiny, trace amounts of water trapped in the minerals of the lunar surface. Some of this water likely comes from solar wind protons, which interact with oxygen in the regolith to form hydroxyls. In permanently shadowed craters near the poles, even actual water ice has been detected. So maybe, just maybe, there's enough of this moisture, combined with those brief exposures to Earth's oxygen, to allow rust to form in the most unlikely place imaginable. And here's another clue. The rust seems more concentrated on the far side of the moon, the side that never faces Earth. That seems backward. Wouldn't the near side get more of Earth's oxygen? But the explanation may lie in the way solar wind interacts with the moon. The near side is more exposed to the sun's particle radiation. Those solar protons bombard the surface and may actually suppress oxidation by knocking away oxygen atoms. But the far side, protected during certain orbital phases, might be where the fragile ingredients for rust are allowed to linger and react. This discovery has huge implications. First, it suggests the moon's surface is more chemically dynamic than we thought, not just inert dust, but a surface where slow, subtle processes are still unfolding. Second, it hints at a strange, invisible connection between Earth and Moon, one that goes beyond gravity. Our atmosphere literally reaches out to the moon, shaping its chemistry for a world we often think of as separate. The moon might be more tied to Earth than we ever realized. But perhaps the strangest part of all is this. Rust doesn't just tell us about the moon as past. It could tell us about its future. Understanding where and how hematite forms could help scientists find pockets of water hidden in the lunar regolith. That's vital information for future lunar missions. If we're going to live on the moon, we'll need to know where to find water, not just for drinking, but for making oxygen and rocket fuel. Rust might be the breadcrumb trail that leads us to those resources. And there's a poetic irony in that. Rust, the ultimate sign of decay on Earth, something we associate with neglect, damage, the breakdown of machines. And metal might actually point the way forward in our quest to explore and colonize the moon. It might mark the locations of water, guide the construction of lunar habitats, and even rewrite our assumptions about what can and can't happen on an airless world. So, yes, there are patches of rust on the moon. Rust where no water should flow. Rust in a place with no air. It's one of the quietest chemical miracles in the solar system. A slow, silent transformation hidden in the dust. Proof that even in the most desolate places, strange reactions can unfold. The moon keeps surprising us, and sometimes it turns red. We picture the moon as solid, silent, and still. A giant ball of ancient rock, pockmarked by billions of years of impacts. But what if, beneath that dusty surface, the moon hides something much more complex? What if it's not just craters and plains, but a hollow world of underground tunnels, some stretching for miles, carved not by aliens or mining machines, but by lava? Because evidence is mounting that the moon may have once been home to massive underground lava tubes, and some of them may still be intact today. Let's rewind 3 to 4 billion years. The moon, back then, wasn't the quiet gray body we see now. It was geologically alive. Volcanoes spewed molten rock across its surface, filling in craters and creating the dark patches we now call Maria, the lunar seas. These vast basalt plains are the result of enormous volcanic eruptions that oozed across the terrain like syrup on a plate. But here's what many people don't realize. Lava doesn't just flow across the surface. It also flows beneath it. And on Earth, that's where lava tubes come into play. Lava tubes form when the outer layer of a lava flow cools and hardens, while the molten rock inside continues to flow downhill, protected by the insulating crust. When the eruption ends and the lava drains out, it can leave behind a long, empty tunnel, essentially a volcanic pipe. On Earth, we find lava tubes in places like Hawaii, Iceland, and the Canary Islands. Some are big enough to walk through. Others are vast enough to drive vehicles through. And based on what we've seen on the moon, it looks like a very similar process may have occurred there, just on a much grander scale. How do we know? It started with something called skylights. These are round holes spotted by lunar orbiters that seem to open into subsurface voids. They don't look like impact craters. They're too smooth, too vertical, and they often sit within ancient lava plains. NASA's Lunar Reconnaissance Orbiter has captured images of multiple skylights, particularly in regions like Marius Hills and the Sea of Tranquility, which strongly suggest the presence of collapsed ceilings leading into empty chambers below. In other words, entrances to lava tubes. Some of these skylights are tens of meters wide. The tubes beneath them could be hundreds of meters in diameter, stretching for miles. One analysis, based on gravity data and surface collapse patterns, estimated that lunar lava tubes could be up to 1,000 meters over half a mile in width. That's larger than any known lava tube on Earth. The lower gravity of the moon helps. It puts less stress on the rock, meaning bigger tunnels can stay intact without collapsing. That makes these structures not just scientifically fascinating, but practically useful. Because here's where things get really interesting. If these tunnels still exist, they might be perfect candidates for lunar habitats. Why? Because the moon is a hostile place. It's bombarded by solar radiation, pelted by micrometeorites, and experiences extreme temperature swings from 127 degrees Celsius, 260 degrees Fahrenheit, in the daytime to minus 173 degrees Celsius, minus 280 degrees Fahrenheit, at night. Building habitats on the surface means shielding astronauts from all of that. But underground, inside a lava tube, you're naturally protected. The thick rock would block radiation, regulate temperature, and shield from impacts. You wouldn't need to build bunkers. The moon already built them for you. Some researchers and space agencies are taking this seriously. Japanese scientists, using data from their Selene orbiter, identified a large potential lava tube under the Marius Hills region. NASA and ESA have both conducted simulations of what life could look like in one of these lunar caves. Some architects have even drawn up concept art for underground bases built within lava tubes, imagining long pressurized tunnels with laboratories, living quarters, and even hydroponic farms, all nestled safely beneath the moon's crust. But these tubes may also hold scientific value beyond habitability. Because they've been sealed off for billions of years, they might preserve a perfect record of lunar geology. The regolith on the moon's surface has been churned, cooked, and blasted by solar wind and impacts. But inside a lava tube, you could find untouched materials, volcanic rock, ancient gases, maybe even water, ice preserved like a time capsule. It's a chance to peer back into the moon's fiery youth, to study how it cooled, how it changed, and what secrets its interior might still hold. Some scientists even speculate that these tubes might connect into larger, more complex networks, a sprawling underground system of lava-carved passageways. On Earth, lava tubes sometimes fork, merge, and form entire cave systems. If the same thing happened on the moon, we might be looking at not just individual tunnels, but a subterranean web hidden beneath the Maria, silent and unexplored. There's still a lot we don't know. No human or rover has ever entered a lunar lava tube. We don't know how stable they really are, how deep they go, or what they contain. But new missions may change that. Future lunar rovers could be equipped to explore skylights, map voids, or even drop sensors into the dark. One day, robotic explorers may enter a tube and reveal what lies beneath. And after that, perhaps humans could follow. Imagine the first time a person descends into a natural tunnel that hasn't seen sunlight in 3 billion years, a place older than any building on Earth. Shaped by alien geology, untouched by life, a place where silence reigns and where the moon keeps its oldest memories. These tunnels aren't just holes in the ground. They're the moon's hidden arteries, remnants of a time when it was alive with fire. And they might just be the key to our future among the stars. So yes, the moon might have a lava tunnel network, not metaphorically, literally miles of hollow space beneath your feet, created by a world that once boiled with volcanic fury. It's not just science fiction. It's science, and it's waiting to be explored. The moon, for all its ancient calm, isn't as lifeless as it appears. During the Apollo missions, astronauts reported seeing something strange, something that didn't match their expectations of a cold, dead world. They saw flashes of light-quick, spontaneous bursts that appeared on or near the surface. Some were brief glows, others looked like sparks or pulses, and they weren't hallucinations or tricks of the eye. These events had been seen from Earth long before astronauts went to the moon, and they're still being reported today. Scientists have a name for them: transient lunar phenomena, or TLPs. Let's start with the astronauts. During Apollo 11, while orbiting the moon in the command module, astronaut Michael Collins noticed a strange, brief glint of light near the surface. It was unlike anything he expected to see. He wasn't the only one. Across other missions, reports trickled in. Flashes, faint glows, localized illuminations that seemed to shimmer briefly and then vanish. These weren't from the spacecraft or instrumentation. They appeared to originate on the moon itself. But the story of lunar flashes doesn't start with Apollo. It goes back centuries. One of the earliest known reports came from William Herschel in 1787, the astronomer who discovered Uranus. He claimed to have seen lights on the moon, describing them as volcanoes. Since then, hundreds of sightings have been logged by professional and amateur astronomers alike, often from observatories, sometimes just from backyard telescopes, all over the moon, but most commonly in specific regions like the Aristarchus crater, a location long associated with unusual activity. These TLPs vary in type. Some are brief, star-like flashes. Others are glowing clouds or shifting patches of light that last several seconds to minutes. Some even appear as color changes, pinkish or bluish hues that momentarily tint the gray lunar surface. They happen suddenly and without any predictable pattern, which makes them incredibly hard to study. Skeptics have long dismissed these reports as atmospheric distortion, visual artifacts, or observer error. After all, viewing a distant surface through Earth's turbulent atmosphere can play tricks on the eye. But then came the Apollo data, and suddenly the stories weren't so easy to dismiss. If astronauts orbiting in the vacuum of space were seeing the same kinds of flashes, then atmospheric distortion wasn't the explanation. Something real was happening on the moon. So, what causes it? There are several competing theories, and none of them are fully confirmed. One possibility is gas release. The moon's surface is constantly pummeled by micrometeoroids. When these tiny space rocks strike, they can release energy, vaporizing a bit of the surface, heating up dust, and maybe even triggering short bursts of trapped gas from deep within the crust. If those gases escape argon, helium, or even radon, they might glow under certain conditions, creating brief flashes or clouds of light. There's some evidence to support this. Instruments placed by Apollo astronauts detected tiny amounts of outgassing in the moon's exosphere, suggesting that while the moon isn't geologically active like Earth, it's not entirely inert either. It may still have localized activity, fault lines cracking under stress, or pockets of ancient gases escaping after billions of years. Another theory points to electrostatic effects. The moon's surface is coated in fine, abrasive dust lunar regolith, which can become electrically charged by solar radiation. When day turns to night, or when shadowed areas suddenly face the sun, that charge can shift. Some scientists believe this might cause dust particles to levitate, or even spark briefly, like static electricity building up and suddenly discharging. These electrostatic events could be luminous enough to cause faint flashes. There's also the possibility of meteoroid impacts, small, high-speed collisions that briefly light up the surface. NASA has actually recorded these using telescopes trained on the moon during meteor showers. When a meteoroid strikes, it releases a bright, fast burst of light. Most of them are too small to detect without sensitive cameras, but some may be visible to the naked eye, especially in the vacuum of space, where there's no atmosphere to dim or blur the effect. But none of these theories fully explain the localized glowing patches and color shifts that some observers have seen. And that's what keeps this mystery alive. TLPs don't follow a neat scientific pattern. They're rare, unpredictable, and difficult to replicate. The moon doesn't give up its secrets easily. And even in the age of satellites and lunar rovers, we still don't fully understand what's happening when these lights flicker on. Modern research has revived interest in these phenomena. In 2019, a team of German researchers installed a robotic telescope in Spain dedicated to observing the moon night after night, hoping to catch TLPs in action. They've captured dozens of candidates' brief flashes, oddly timed glows, and localized events near known craters. The data is being analyzed frame by frame. And while many flashes are likely meteoroid impacts, some remain unexplained. And then there's the location factor. Certain regions, especially Aristarchus, Plato, and Kepler craters, seem to be hot spots. They get more reported TLPs than other areas. Is it coincidence, optical illusion, or do these places represent geological weak points, areas where stress or heat or gas might still be breaking through to the surface? Future missions may provide answers. If we land robotic probes or human bases near these regions, we may finally observe TLPs from the ground, or even catch one in progress. High-sensitivity seismic and electromagnetic instruments could reveal what's really happening beneath the surface. But for now, we're still guessing. What we do know is this: the moon isn't just reflecting sunlight. It sometimes emits its own not as a sustained glow, but in sudden, mysterious bursts. The kind that makes you blink and wonder if you really saw anything at all. The kind that makes astronauts glance at the surface and say, "Wait, did you see that too?" Yes, they did, and so have we. The moon flashes. Sometimes it flickers. And in those brief, bright moments, it reminds us that we don't know it as well as we think we do. That even a world we visited, mapped, and stood on still holds secrets written not just in stone, but in light. It hangs silently in the sky, just a glowing disk of rock 384,400 kilometers away. It doesn't make noise. It doesn't move quickly. And yet, for millennia, people have believed that the moon somehow influences life down here on Earth. Not just tides or calendars, but us, our minds, our moods, our biology. And the strange thing, the more science investigates it, the harder it becomes to dismiss. Because while the moon isn't casting spells or whispering in our ears, there is growing evidence that it really does affect animal behavior. And yes, even human behavior too. Let's start with the obvious. The moon's gravitational pull moves oceans. Tides are its most well-known influence, and they're massive. Twice a day, seawater bulges and recedes because of the moon's constant gravitational tug on our planet. That part's not mysterious. It's physics. But tides don't just stop at the shoreline. They influence entire ecosystems. Many animals have evolved to sync their lives to the lunar cycle, from birth and feeding to migration and reproduction. Take the grunion, a small, silvery fish native to the Pacific coast. These fish time their spawning to the full and new moons. During high tide, they come ashore in massive waves, wriggling up the sand to lay and fertilize eggs. Then, 2 weeks later, when the tides rise again, the baby fish hatch and are washed back into the ocean. It's a perfect rhythm, guided by nothing but moonlight and gravitational cycles. Or the corals of the Great Barrier Reef. These ancient creatures, stationary, mind you, somehow know when the full moon hits. Once a year, in a synchronized planetary event, they release their gametes into the water in massive glowing clouds. It's a lunar scheduled spawning event, so precise that it can be predicted down to the hour. No clocks, no weather cues, just the moon. Even land animals aren't immune. Lions in Africa hunt more successfully during darker phases of the moon, when their prey can't see them as well. Wolves howl more frequently near the full moon, not because of mythology, but likely due to higher levels of night activity. Birds migrate using lunar cues. Nocturnal insects shift their feeding patterns with moonlight. It's not just legend, it's evolution. The moon, for millions of years, has been a clock in the sky, and life, at every level, has learned to tell time by it. So, what about humans? Surely we're above all that modern, electrically, scientifically minded. We don't spawn with the tides or hunt by moonlight. And yet, the full moon has always had a mythic grip on the human psyche. In folklore, it's tied to madness, transformation, crime, even birth. The word lunatic comes directly from luna, Latin for moon. For centuries, doctors believed full moons triggered seizures, mental illness, even violent behavior. Werewolves, witches, rituals, all linked to the lunar cycle. You'd think science would have debunked all of that by now. And to some extent, it has. Large-scale statistical studies have tried to correlate lunar phases with visits, psychiatric admissions, birth rates, crime spikes, and more. The results, inconclusive at best. Most studies show little or no significant effect, and yet, some still hint at a subtle pattern not strong. Not every month, but enough to make researchers pause. In 2013, a study published in Current Biology found that participants in a controlled sleep lab took longer to fall asleep and got less deep sleep during the full moon, even though they couldn't see the moon and had no idea what phase it was. Their melatonin levels dropped, and brain activity showed signs of disrupted circadian rhythms. It wasn't psychological. It was physiological. Other studies have found slightly increased rates of seizures, anxiety, or depressive symptoms near the full moon in certain patients. Again, not dramatic shifts, but measurable ones. Some researchers believe the moon's effect on sleep may, in turn, affect mood, cognition, and behavior. After all, even a mild disruption in rest can cascade into emotional changes. And for people already vulnerable to mental health issues, that little nudge might matter. There's also light to consider. A full moon can be bright enough to suppress melatonin, the hormone that regulates sleep. Even before artificial lighting, early humans would have experienced much brighter nights during full moons. That might have evolved into behavioral shifts, staying awake longer, hunting more, gathering under moonlight. In that sense, the moon could have shaped not just our biology, but our culture. And birth, that's my favorite topic. Ask any nurse or obstetrician if full moons lead to more deliveries, and many will swear it's true. Studies are mixed. Some show slight increases in spontaneous labor near full moons. Others show no effect at all. But the belief persists, not because it's proven, but because it's observed again and again in anecdotal patterns. Maybe the moon doesn't cause labor, but maybe it coincides with environmental changes, light levels, gravitational shifts that subtly influence our bodies. Even animals that live in urban environments, completely removed from nature, seem to respond to the lunar cycle. Studies of rodents, pets, and zoo animals have found changes in activity levels, aggression, and sleep behaviors that line up loosely with the moon's phases. We don't always know why. We just know it happens. So no, the moon doesn't turn people into werewolves or drive them mad once a month, but it does nudge things gently, quietly, like a second hand ticking on a biological clock. It tugs at fluids, hormones, instincts, sometimes through gravity, sometimes through light, sometimes in ways we haven't figured out yet. The moon isn't the master, but it's not a passive observer either. It's a celestial influencer, shaping tides, migrations, sleep cycles, and maybe even emotions, not with force, but with rhythm. A rhythm that life has been listening to for billions of years. And even if we've forgotten how to hear it, it's still playing quietly in the background of every living thing, including us. For decades, the moon was considered a bone-dry desert, a place scorched by sunlight, stripped of atmosphere, and utterly devoid of something as fragile as water. That belief held strong even after Apollo astronauts returned with lunar samples. The rocks they brought home seemed dry, and early tests didn't show any trace of water molecules. The moon was dust, stone, and vacuum. That was the story. But the story was wrong. Because not only is there water on the moon, it's there in more places and stranger forms than anyone expected. And the deeper we look, the weirder the truth becomes. Let's start with the most surprising twist. The Apollo rocks actually did contain water. We just didn't know how to look for it. The instruments used in the 1970s weren't sensitive enough to detect water trapped deep inside the rock structure. Later, when scientists reanalyzed the samples using more advanced methods, they discovered tiny inclusions, microscopic volcanic glass beads that held molecular water. That's right, the moon wasn't just hit by water-rich asteroids. It had volcanic eruptions that produced water-bearing magma. That means the moon's interior, at some point, had water baked into it. But that's just the beginning. In 2009, NASA deliberately crashed a probe, the LCROSS impactor, into a permanently shadowed crater near the moon's south pole. These craters never see sunlight, not even once. The temperatures inside can drop to minus 250 degrees Celsius, minus 420 degrees Fahrenheit, cold enough to freeze not just water, but many volatile substances. When LCROSS hit the surface, it kicked up a plume of material, and inside that plume, clear spectral signatures of water ice, a lot of it. That moment shattered the dry moon myth once and for all. These cold traps at the poles, hidden in eternal darkness, are littered with ice, not puddles, not lakes, but frozen grains and sheets mixed into the lunar soil. Some estimates suggest there could be hundreds of millions of tons of water ice locked inside those craters. But here's where it gets weird. That's not the only water on the moon. In 2018, researchers using data from NASA's Moon Mineralogy Mapper confirmed something unexpected. There's water spread across the surface of the moon, even on the sunlit side. That discovery blew the doors open. How could water survive in direct sunlight on an airless body where temperatures reach over 120 degrees Celsius, 250 degrees Fahrenheit? The answer lies in how the water is stored. It's not liquid. It's not even really ice in the traditional sense. Most of this water exists as hydroxyl, O molecules, chemically bonded to the minerals in lunar soil. It's not puddled or frosted. It's trapped at a molecular level, clinging to silicate grains. Some of it may also exist as nanobeads of ice hidden inside tiny voids in the regolith, surviving only because they're shielded from direct heat. And it's not evenly distributed. Water seems to shift over the course of a lunar day. When temperatures rise, some of it may migrate or sublimate. When night falls, it may recondense and get trapped again. That means the moon has a kind of quasi-water cycle, incredibly slow, incredibly subtle, but present, a migration of molecules that moves with light and shadow. Another clue to the water mystery came from India's Chandrayaan-1 mission. Its data showed hydroxyl-rich areas clustered around high-latitude regions, far from the equator. These are places that still see sunlight, but not as intensely. And they may provide a middle ground where water can stick around without being blasted away. So, where did all this water come from? There are three main possibilities. Comet and asteroid impacts, these icy visitors, have been slamming into the moon for billions of years, and some of the water from those impacts could have been buried in cold traps before it had a chance to escape into space. Solar wind reactions, this is perhaps the strangest source. The moon's surface is constantly bombarded by hydrogen ions from the sun, particles traveling at high speeds, and when these hydrogen atoms strike lunar soil, they can react with oxygen in the rock to form hydroxyl, O, or even H2O. It's a kind of space weather chemistry driven entirely by solar energy. Volcanic origin, some of the water may have been native to the moon, trapped inside during its formation, then released in ancient lava flows. The discovery of water in lunar volcanic glass supports this theory, suggesting the moon's interior wasn't always as dry as we thought. What's amazing is how this water, in all its forms, is changing the future of lunar exploration. NASA's Artemis program is targeting the South Pole for future crewed landings, precisely because of the water ice locked in its shadows. That ice could be harvested, melted, purified, even split into hydrogen and oxygen to make rocket fuel. Water isn't just for drinking. It's the foundation of self-sustaining exploration. But harvesting it won't be easy. The ice is mixed with dirt, buried under regolith, and stuck in brutal terrain with no sunlight. Mining it will require new technology drills, rovers, heating systems, and protective habitats. The hydroxyl-bound water, spread across sunlit terrain, may be even harder to access. You'd have to bake it out of the soil molecule by molecule. Still, the fact that it's there at all is astonishing. For a place once thought to be drier than bone, the moon is turning out to be a complex, evolving water world, just one where the water is hiding in the shadows, clinging to rocks or drifting molecule by molecule in the thin exosphere. It's not Earth. It's not Mars. It's its own strange alien system. And it holds just enough water to keep scientists guessing and explorers dreaming. So yes, the moon has water, but not like we imagined. It's trapped, frozen, chemically bound, and alive with motion. A ghost of a water cycle playing out across a dead world. And now that we know it's there, we'll never look at that silent, gray sphere the same way again. The moon looks smooth and symmetrical from afar, perfect sphere orbiting Earth with slow, steady grace. But that illusion falls apart when you get up close, because the moon's gravity is not uniform. It's lumpy, uneven, in some places inexplicably stronger, in others strangely weak. And these gravitational anomalies aren't just quirks. They're so powerful, they once crashed spacecraft. Even today, they remain one of the moon's strangest unsolved puzzles. Here is what you need to know. Gravity on the moon isn't smooth like it is on Earth. If you flew over the moon with a very sensitive scale, it would fluctuate constantly. In some places, you'd weigh noticeably more than you would just a few kilometers away, without gaining a single atom. That's because of something scientists call mass concentrations, or maskins. Maskins are areas of the lunar crust where there's more mass than expected, usually buried deep below the surface. They tug harder on spacecraft, satellites, and even orbiting debris. The pull is subtle, but cumulative. If you don't account for them in your calculations, a probe flying over one can slowly spiral out of orbit or slam into the ground, as several unlucky missions learned the hard way in the early days of lunar exploration. The existence of maskins was first confirmed in the 1960s, when NASA's lunar orbiter missions, precursors to the Apollo landings, began behaving strangely. Their orbits, predicted with precision, kept shifting. Something was tugging on them, something invisible. Eventually, scientists realized these odd accelerations were caused by hidden concentrations of mass beneath the moon's surface. What is even stranger is where these maskins show up, mostly beneath the moon's largest impact basins, the dark, circular maria we see from Earth places like Imbrium, Serenitatis, Crisium, and Humorum. These enormous craters, created by asteroid impacts billions of years ago, were later filled in by lava flows. But something beneath them, something deeper than just solidified lava, seems to be incredibly dense. One theory is that after the impact, the moon's crust cracked, and molten rock from the mantle surged upward, pooling and cooling in ways that created these anomalies. Another theory suggests that chunks of asteroid core ultra-dense fragments remained buried under the surface. Or maybe the impacts themselves compressed the lunar mantle below, concentrating mass like a bruise that never healed. But here's the thing, we still don't know for sure. In 2011, NASA launched the Grail Mission 2 spacecraft, named Ebb and Flow, flying in tight formation around the moon. Their job was to map the moon's gravitational field in unprecedented detail. And what they found was stunning. Not only are maskins more widespread than we thought, but the moon's entire gravitational landscape is a chaotic mess of highs and lows, as if someone wrinkled the crust from the inside out. These gravity maps revealed hidden structures beneath the surface, ancient lava tubes, buried faults, even remnants of the moon's once molten core. The data confirmed that the moon is not just a dead rock, but a geologically complex body shaped by forces we're still trying to decode. GRIL showed that some maskins are twice as dense as the surrounding material, concentrated in tight, bullet-shaped regions deep beneath the crust. This uneven gravity has practical consequences too. Any future lunar base, rover, or satellite has to navigate a gravitational field that doesn't behave intuitively. A spacecraft in low orbit around the moon can't just glide in a neat circular path. It gets yanked, drifted, pulled slightly off course, depending on what's below. Engineers now build these variations into their models, but early missions weren't so lucky. The Soviet Luna 15 spacecraft, racing the Apollo 11 mission in 1969, crashed into the moon, in part due to unaccounted for gravitational shifts. Even today, GRAI, Loud's gravity data is being used to refine landing sites for future missions. If you don't know what's tugging on your lander, you don't know how fast you're falling. And in a world where the difference between a soft touchdown and total destruction can come down to a few seconds, knowing your gravitational terrain is everything. There's also a deeper mystery here. Why is the moon's gravity so uneven, but Earth's isn't? Earth has volcanoes, mountain ranges, and tectonic plates, much more dramatic geology, but its gravity is surprisingly smooth. The moon, by contrast, seems frozen and static. Yet beneath its surface lies this bizarre patchwork of invisible anomalies. One possible answer is age. The moon has no atmosphere, no erosion, no tectonics, so its scars are permanent. Every impact, every magma surge, every buried mass is preserved, layered like a time capsule. Earth's surface, by contrast, is constantly refreshed by weather, water, and plate movement. So, gravity smooths itself out over time. The moon is a fossilized snapshot of its own chaotic past. And, in a poetic twist, the same gravitational quirks that once confused scientists and wrecked spacecraft might one day help us. Maskins could be signposts for ancient heat flow, mineral concentrations, or even trapped volatiles deep underground. In the same way that gravity maps of Earth help locate oil, gas, and underground water, detailed lunar gravity surveys might help future explorers find natural resources hidden just beneath the surface. So the next time you look up at the moon and see its serene face staring down, remember, it's not a perfect sphere. It's a place of invisible forces, where gravity itself bends and twists in strange, unexpected ways, a world shaped by ancient violence, frozen in time, and still tugging on everything that dares to orbit too close. The moon's gravity is uneven, and it's not just a curiosity. It has a message from the deep interior of a world that still has secrets to pull from the shadows. One of the strangest, most overlooked facts about the moon is also one of the most obvious. We always see the same face. Every night, for every person on Earth, the moon presents the same familiar features. The sea of tranquility, the ocean of storms, the man in the moon. It doesn't spin in the sky like a globe. It doesn't reveal its far side from Earth. Half of it is always turned toward us, and half is always turned away. And no, that's not just a fluke of geometry. It's not some visual trick. It's real, and it's intentional, not in the sense of design, but in the way the laws of physics have locked us into this cosmic embrace. The phenomenon is called tidal locking, and while it might sound like a gentle, passive process, it's actually the result of a gravitational tug-of-war that's been playing out for billions of years. To understand it, you need to think about how gravity behaves over time, not just as a force that pulls things together, but as a force that reshapes them subtly and relentlessly. In the moon's early days, it spun much faster. Its rotation didn't match its orbit around Earth. If you were alive back then, which you weren't, because Earth was a molten hellscape, you'd have seen different parts of the moon's surface over time. But as the moon orbited Earth, Earth's gravity kept pulling on the bulge created by the moon's slightly squashed shape. Imagine a potato instead of a perfect sphere. That gravitational pull acted like a brake. Over millions of years, Earth's gravity slowed the moon's rotation until it matched the time it takes to complete one orbit. Once that happened, something strange occurred. The gravitational tug stabilized. The moon became tidally locked, and from that point forward, one hemisphere always faced Earth, and the other, the far side, never did. This isn't unique to our moon. Tidal locking happens all over the universe. Many of the moons of Jupiter and Saturn are tidally locked to their parent planets. Even some exoplanets are thought to be tidally locked to their stars, with one face permanently roasting in sunlight, the other plunged in eternal darkness. It's a consequence of angular momentum and energy dissipation. It's nature's way of settling into balance. But here's where the moon gets special. Most tidally locked bodies don't have observers on the other side. We do. We're here on Earth, watching this quiet partner in our sky, and it's showing us just one face. That fact alone has shaped everything about how we perceive it. Our myths, our stories, our scientific exploration, all based on the same familiar terrain. Before we sent spacecraft around the back, we literally had no idea what the far side of the moon looked like. In fact, it wasn't until 1959, when the Soviet spacecraft Luna 3 took the first blurry images of the moon's hidden half, that humanity saw the far side for the first time. And it was weirdly different. More craters, fewer Maria, an entirely different landscape. The same moon, yes, but with a completely different personality. It was like discovering your quiet neighbor had an entire secret life you never knew about. So, why doesn't the moon flip around? Why doesn't anything disturb the lock? Well, it actually does wobble a little something called libration. Because the moon's orbit around Earth isn't a perfect circle, it's slightly elliptical. And because of the tilt of its axis, we can see about 59% of the moon's surface from Earth over time, not just 50%. It's like the moon nods and rocks, ever so slightly revealing a little more along the edges. But the core idea remains. We always see the same central face because the moon's rotation is perfectly synchronized with its orbit. And that's no accident. It's the natural end state of any close gravitational relationship over enough time. The Earth is actually experiencing the same effect in reverse. The moon is gradually slowing Earth's rotation too. And in the far distant future, billions of years from now, Earth may also become tidally locked to the moon. At that point, one side of Earth would always face the moon, and the other would never see it again. Imagine that. But there's another layer here, something more poetic. The fact that the moon always shows us the same face means that human history was shaped by just one version of the moon. We told stories based on its visible markings. We chose landing sites based on familiarity. We pointed telescopes at it, stared at it, dreamed about it all from the perspective of a partial truth. The far side remained a mystery. And even now, despite satellites and landers, that asymmetry still shapes how we relate to our nearest neighbor. It also raises strange questions. What if we had evolved on a planet without a tidally locked moon? What if we could see all sides of the moon from Earth? Would we have developed the same relationship to it, the same myths, the same fascination? Probably not. Tidal locking made the moon feel constant, like a face in the sky that watches us endlessly. It gave the moon personality. And that face, it's deeply familiar. Whether you see a man, a rabbit, or something else entirely, it's been watching us for as long as we've had eyes to look up. It hasn't changed. And that strange gravitational coincidence is the reason why. So yes, the same side of the moon always faces us. And no, it's not random. It's the result of billions of years of physics, friction, and gravitational tension. It's a balance so perfect, it feels like design. But it's just nature working quietly in the background. One spin per orbit, one face forever, turned toward Earth. Not a coincidence, a cosmic commitment. If the moon vanished tomorrow, not exploded, not collided with Earth, just quietly blinked out of existence, the consequences would be apocalyptic. Not because of tides, though those would vanish too. Not because the nights would get darker, though they would. The true catastrophe would come in something most people never think about: Earth's tilt. Right now, our planet's axis is tilted at about 23.5. That tilt is the reason we have seasons. As Earth orbits the sun, different hemispheres lean toward or away from the light, creating the cycle of spring, summer, fall, and winter. Without axial tilt, you wouldn't have summer in Australia, while it's winter in Europe. You'd have one endless climate based on latitude. Cold at the poles, hot at the equator, and no variation. But here's the part that's terrifying. That tilt is not fixed. It wobbles slowly. Over thousands of years, Earth's axis drifts in a cycle called axial precession, like a spinning top that begins to lean. On its own, Earth's tilt could shift wildly, swinging from 0 to 85 over geological time. And if that happened, the consequences for life would be catastrophic. Deserts would become tundras. The poles could rotate into the tropics. Rain patterns, ocean currents, ice caps, all of it would be thrown into chaos. So why doesn't that happen? Because of the moon. The moon acts like a stabilizer, a giant counterweight orbiting Earth, applying constant gravitational torque that helps keep our axial tilt relatively steady. Instead of swinging chaotically, Earth's tilt only shifts by about 1.3 over 41,000-year cycles. That small variation is what allows ice ages and interglacial periods to rise and fall gently, not apocalyptically. In a very real sense, the moon is the reason Earth as climate has been relatively stable for billions of years. Stable enough for life to not only emerge, but to thrive. Scientists have modeled what Earth would look like without the moon. And the picture isn't pretty. Without lunar stabilization, simulations show Earth's tilt could vary between 10 and 85 degrees. At the high end of that scale, the planet could essentially roll over on its side. Imagine the North Pole pointing straight at the sun for months on end, baking in 24-hour daylight while the equator plunges into freezing darkness. It would be a climatic nightmare. Ecosystems would collapse. Mass extinctions would be inevitable. And the moon's mass is the perfect size for this role. It's unusually large for a planetary satellite, a quarter the diameter of Earth, with a surprising amount of angular momentum. Most other planets in our solar system have tiny moons, or none at all. Mars, for example, has Phobos and Deimos-captured asteroids barely big enough to hold their shape. They do almost nothing to stabilize Mars, which is why Mars' tilt is wildly unstable, ranging from 10 to 60 over time. And it shows. Mars has been through dramatic climate swings, with ice caps that migrate, ancient riverbeds that run dry, and no consistent pattern of stability. It's a reminder of what Earth could have been. So, how did we get so lucky? Most scientists believe the moon was born from a colossal impact. Around 4.5 billion years ago, a Mars-sized planet, often called Theia, slammed into the early Earth. The debris from that collision formed a ring of molten rock, which coalesced into the moon. Because it formed from Earth's outer layers, the moon ended up with a similar composition, but enough mass and angular momentum to influence Earth's long-term behavior. That impact may have created the very conditions necessary for life, not just by giving us tides and light, but by locking in Earth's axial stability from the start. In other words, if Theia had missed, we might not be here. It's a subtle kind of miracle. The moon doesn't warm the planet or make air breathable. It doesn't carry life or provide food, but it shapes the stage on which life can exist. By preventing extreme climatic swings, it allows evolution to proceed without being reset by global catastrophes every few million years. It lets forests grow, civilizations rise, ecosystems persist long enough for complexity to emerge. It buys us time to adapt, change, survive. Even today, the moon continues its stabilizing work. Quiet, steady, unfailing. Without it, climate models show Earth could become unrecognizable within a few thousand years. With it, we continue to orbit in a cosmic balance that seems mundane until you realize how fragile it really is. So the next time someone calls the moon boring or lifeless, or just a dusty rock, remind them, that dusty rock is the reason we're not extinct, the reason Earth isn't a frozen spinning marble or a scorched wobbling furnace. The moon's presence makes Earth like, and without it, the planet you're standing on might not be livable at all. The moon doesn't just orbit us, it anchors us. Look up at the moon tonight. It's a calm, familiar presence, steady in its orbit, always the same size, the same silver face. It feels permanent, fixed. But the truth is, the moon hasn't always been where it is now. In fact, it used to be much, much closer, so close, it would have filled the sky like a glowing monster. And when it did, Earth was a very different place, with 5-hour days, massive tides, and a spin so fast, the planet might have made you dizzy. To understand this, we have to go back to the moon's beginning, back to that colossal impact that formed it roughly 4.5 billion years ago. A Mars-sized body, Theia, slammed into the early Earth. The debris ejected from the collision eventually coalesced into the moon. But the moon didn't form out there at a cozy 384,400 kilometers. No, in those early days, the moon hovered just 20,000 to 30,000 kilometers above Earth's surface, about 14 times closer than it is today. That close, it would have looked absolutely enormous in the sky, maybe 20 times bigger than it appears now. You wouldn't have needed a telescope to see details. You would have seen the ridges, the shadows, the slow-motion spin of a planet-sized object orbiting at terrifying speed. But the moon's proximity didn't just change the view. It fundamentally altered the way Earth behaved. Because the moon was close, its gravitational pull on Earth was much stronger, strong enough to create colossal tides, not just in the oceans, but even in the young Earth's partially molten crust. These were tides that could rise hundreds of feet, triggering earthquakes and volcanic activity. The planet was constantly flexing, bulging, and shifting under the moon's influence. The Earth and moon were locked in a violent gravitational dance, exchanging energy, reshaping each other in real time. And one of the biggest effects was on Earth's rotation. Today, Earth spins once every 24 hours. But back then, it was spinning roughly once every 5 hours. That means a full day, sunrise to sunrise, was just a fifth of what we experience now. The sun would rise, arc across the sky, and set again in what we'd think of as a long afternoon. Nights and days came fast. Winds were fiercer. Weather systems moved rapidly. The planet was in hyperdrive. So what changed? Tidal friction. As the moon pulled on Earth's oceans, it created a bulge that didn't align perfectly with the moon's position in the sky. Because Earth was spinning faster than the moon's orbit, the ocean bulge led the moon slightly, tugging forward on it. That forward pull gave the moon a boost of angular momentum, pushing it into a wider orbit farther from Earth. But conservation of energy demanded a trade-off. As the moon moved away, Earth's rotation slowed down. It still is. Even today, the moon continues to recede from Earth at a rate of about 3.8 centimeters per year. That's roughly the speed your fingernails grow. It doesn't sound like much, but over millions of years, it adds up. Geological records, coral growth patterns, and tidal rhythms all show the evidence. Earth's days used to be shorter, and the moon used to be closer. In fact, we can track it. 620 million years ago, days were about 21.9 hours long. 900 million years ago, about 18 hours. Go back 4 billion years, and Earth spun so fast, days lasted just 4 to 6 hours. In the distant future, if this trend continues long enough, Earth and Moon will become mutually tidally locked, meaning Earth will eventually always show the same face to the Moon, just as the Moon does to us now. But we're not there yet. For now, the Moon continues to inch away, like a partner in a slow cosmic dance. Each year, it climbs a little higher, slows Earth a little more, stretches time ever so slightly. It's a process so slow, we'll never notice it in our lifetimes. But on a planetary scale, it's monumental. And this drifting moon, this ancient movement, may have been essential for life. Those violent tides from the early Earth, they might have helped mix the oceans, distributing heat and nutrients, stirring the chemical soups that eventually gave rise to life. And the slowing of Earth's spin brought more stable climates, longer days, and more time for biological rhythms to evolve. The moon wasn't just shaping the oceans, it was shaping biology. So that pale, quiet moon you see in the sky, the one that seems frozen in time, is actually moving, changing, and always has been. It was once so close, it would have lit up the night like a second sun. It slowed Earth down. It stretched our days. It moderated our climate. It may have even made life possible. We live in the aftermath of that motion, in a world that's been calmed and balanced by something once violent, once monstrous, and now beautiful. The moon was once close enough to dominate the sky, and in its slow retreat, it gave Earth something precious: time. The moon feels like a singular presence, our one constant celestial companion, orbiting Earth in perfect silence. It's so ingrained in human experience that we just call it the moon, as if there could never have been another. But what if that assumption is wrong? What if, long ago, Earth had not one moon, but two? And what if the second one didn't just disappear, but merged with the one we see today? This is not science fiction. It's a real hypothesis, proposed by planetary scientists to explain some of the moon's strangest features. And it begins with one of the biggest puzzles in lunar geology: why the far side of the moon is so weird. You see, the side of the moon we always see from Earth, the near side, is quite different from the far side. The near side has large, dark plains called Maria, ancient lava flows that filled in lowlands and gave the moon its man-in-the-moon face. The far side, on the other hand, is heavily cratered, mountainous, and almost completely devoid of Maria. It's thicker, rougher, and more heavily battered by impacts. Why such a dramatic difference? Enter the double moon hypothesis, first proposed in 2011 by planetary scientists Martin Jutzi and Eric Asfog. According to their model, Earth may have once had two moons: a primary moon, the one we still have, and a smaller companion moon, only about 1,000 kilometers wide. Both would have formed from the same debris cloud left behind by the massive impact with Theia that originally birthed the moon. In this scenario, the two moons orbited Earth in a kind of gravitational truce for millions of years. But orbital systems like that are unstable. Eventually, the smaller moon, the little sibling, began to spiral inward, slowly drifting toward its larger counterpart, not in a catastrophic collision, but in a low-velocity impact, something more like a slow-motion cosmic pancake crash. The theory suggests that, instead of blasting a giant crater or breaking the moon apart, this small moon may have spread itself like frosting across one hemisphere, likely the far side, adding a layer of mountainous crust that made that side thicker and rougher than the near side. This could explain one of the moon's strangest asymmetries. Its crust is about 10 to 15 kilometers thicker on the far side. That's a huge difference. And the far side is so elevated and rugged that scientists have struggled for decades to understand what caused it. A gentle merger with a second moon could be the missing piece. Computer simulations back this up. Models of two moons in a shared orbit show that such a merger is possible, especially if the smaller moon hit the larger one at a glancing angle at relatively low speed, something under 3 kilometers per second. That's slow by cosmic standards, and it has the kind of impact that would undestroy the larger moon, but could redistribute material across one hemisphere. And while this hypothesis is still debated, elegantly ties together several strange lunar facts: the crust thickness discrepancy between the near and far sides, the lack of Maria on the far side, the elevated topography and highlands on the moon's back face, the strange internal layering seen in seismic data and Grail gravity maps. Of course, the second moon, if it existed, is long gone. It left no distinct core, no obvious rubble, only its geological fingerprint smeared across the surface of its sibling. And because this would have happened over 4 billion years ago, confirming it is difficult. we'd need direct samples from the far side's highlands, analyzed with extreme precision, to look for chemical anomalies that might support the theory. Still, the idea of a lost moon isn't that far-fetched. Planetary systems are chaotic places. Mars may have had additional moons in the past. Saturn and Jupiter have constantly shifting swarms of captured objects. And Earth, too, occasionally picks up temporary mini-moons, small asteroids that drift into orbit for a few months or years before flying off again. So, the idea that Earth may have once had two natural satellites, born from the same ancient collision, is well within the realm of possibility. In fact, some scientists believe that multiple moons may be a normal stage in a planet's evolution. After a massive impact, debris doesn't necessarily form just one object. It may create a cloud of fragments, some of which merge, some of which escape, and some of which stick around for a while before meeting a fate like a hypothetical second moon. So the moon we know today may be a composite, not just a relic of an impact, but the final survivor of a lunar sibling rivalry, the last moon standing after a slow and ancient collision erased the other. Its smooth face and rugged back may tell the story not of one world, but of two, fused in silence billions of years ago. There may have been a second moon, and in a way, it's still with us, just no longer separate, just buried in crust and memory and myth. The moon is so deeply woven into our existence that it feels eternal. It lights our nights, shapes our tides, guides our calendars. It has watched over every civilization we've ever known. But across the ancient world, in mythologies and oral traditions, there are stories of a time before the moon existed, an era when the sky was different, when the moon was not yet there. And these tales come not from just one culture, but from many, spread across continents, long before telescopes or modern science. Could they be metaphor, misinterpretation, or could they, in some strange poetic way, preserve a collective memory of the pre-lunar sky? Let's start with the most direct accounts. The Greeks had a word for it, proselyne. It means before the moon. The Arcadians, an ancient tribe from the mountainous central Peloponnese, were called proselynes by later Greek historians. According to legends, they lived in the time before the moon hung in the sky. Even Aristotle referenced this in his writings, describing people who inhabited the land before there was a moon in the heavens. These weren't just metaphors. The stories presented the moon's arrival as a definable event. Far away, in Colombia, the Muisca people had a similar tradition. In their mythology, there was once a time when the moon was absent from the sky and the world was plunged into chaos. Then came a goddess Chia, who rose into the sky and became the moon, bringing order to the calendar and balance to the world. It was a kind of celestial birth story. The moon didn't always exist. It arrived. In Zulu oral tradition from southern Africa, there are strikingly similar themes. Some Zulu elders have passed down stories claiming that the moon was brought into existence by two brothers, Wayne and Mpangu, deities who ruled the moon across the sky. Before that, they say, there was no moon, only darkness at night. Again, the moon is not permanent. It's an event, something that changed the nature of the sky. Even among the Inuit, there are old tales of the time before the moon. In some versions, the moon was once a human figure, chased into the sky or born from an earthly event. In others, it's described as a recent addition to the heavens, not as a timeless object, but something that wasn't always there. What are we supposed to make of this? It's easy to dismiss these as myth, allegory, or symbolic language. Ancient people had rich imaginations, after all. But the fact that so many unrelated cultures separated by oceans, languages, and centuries shared the idea of a time before the moon is curious, especially considering that most other celestial bodies, stars, the sun were always treated as eternal in myth, but not the moon. Some researchers believe these traditions may encode deep time memory fragmented stories passed down from oral cultures that observed the sky thousands of years ago, possibly even predating the formation of written history. Others suggest that these stories reflect cataclysmic sky events like eclipses, meteor showers, or changes in the moon's orbit or brightness that were interpreted as the moon arriving or changing. And then there are those who push the idea further, suggesting that early humans or even proto-humans may have actually lived in an era before the moon formed. They point to the fact that the moon was likely born 4.5 billion years ago, but complex life and intelligent observers only emerged in the last few million. So, that timeline doesn't match. But they argue, if the moon formed more recently than we think, perhaps from a late collision or orbital capture, could humans have witnessed its appearance? This is fringe territory. The prevailing scientific consensus is that the moon formed early, soon after Earth itself, from the Theia impact. There is no mainstream evidence suggesting the moon arrived late enough for humans or human ancestors to witness it. But alternative thinkers cite things like the moon's strangely circular orbit, its synchronized rotation, its odd composition, and the unusual speed of its recession from Earth as potential clues that something about its origin is still misunderstood. Others argue that the stories might describe a time when the moon was barely visible, perhaps obscured by dust or not yet fully captured into its current orbit. Or perhaps these tales arose after dramatic celestial events, like a massive eclipse or a particularly bright meteor, that gave the illusion of the moon being born anew. Still, even within accepted geology, there is a time when Earth existed without the moon. In the first 30 to 100 million years after the planet formed, if intelligent life had existed, then which it didn't, it really would have seen a sky without a moon. Perhaps these ancient stories are simply cultural echoes of that fundamental truth, that the moon is not eternal. It came from somewhere, and it wasn't always here. Regardless of the origin, what's undeniable is that humans across the globe have preserved this idea that the moon arrived, emerged, or was created in a way that marked a turning point in time. And maybe that's not so far from the truth. Because even if the moon formed billions of years ago, its effect on Earth, on tides, climates, fertility cycles, night vision, mythology was so profound that its presence really did change everything. A time before the moon may not be something we can witness, but it's something ancient people remembered or imagined or sensed in some deep way. And in that mystery, they may have preserved a truth modern science is still unraveling. The moon is not just part of the sky. It is a phenomenon, one that began somewhere, sometime, and left a permanent mark on the story of life on Earth. When we picture the moon, we imagine a place of pure silence, a lifeless world where the sky is pitch black, the stars never twinkle, and there's not even a whisper of wind. And for the most part, that's accurate. The moon doesn't have a breathable atmosphere, or clouds, or weather. But here's the twist. It does have an atmosphere. It's just not like anything we experience on Earth. It's so thin, so ghostly, that scientists didn't even recognize it at first. It's called an exosphere, and it's one of the strangest, most delicate features of the entire lunar environment. Let's start with what an exosphere actually is. Unlike Earth's thick, multi-layered atmosphere, where air pressure, temperature, and composition change with altitude, an exosphere is more like a scattered shell of individual particles barely clinging to the surface. There's no air to breathe, no density to speak of, and no real pressure. It's not a fluid like Earth's air. It's a highly rarefied plasma cloud where atoms and molecules are so far apart they almost never collide. If Earth's atmosphere is like an ocean, the moon's exosphere is like a fine cosmic mist, thin enough that each particle travels kilometers before it bumps into anything else. In fact, the moon's exosphere is so sparse that the total mass of it is only about 10 metric tons. That's less than a fully loaded school bus spread over the entire moon. At its thickest, there are only about 100 molecules per cubic centimeter. Compare that to Earth's atmosphere at sea level, which has about 10 billion molecules per cm cubed. That means the moon's exosphere is a trillion times thinner than what we're used to. It's as close to a vacuum as nature gets. And yet, it's there. Discovered in part by instruments left by Apollo missions, and later confirmed by robotic probes, this exosphere contains a strange mix of elements. Among them, helium, likely coming from the solar wind, a constant stream of charged particles from the sun. Argon, a noble gas seeping up from the moon's interior, likely released during slow radioactive decay. Sodium and potassium, which are particularly unusual and are probably kicked up from the surface by micrometeorite impacts and solar radiation. Hydrogen, oxygen, and even trace amounts of water vapor, possibly created by interactions between solar particles and lunar soil. Unlike Earth's atmosphere, which is held tightly by gravity and circulates continuously, the particles in the moon's exosphere don't follow normal atmospheric behavior. They fly in ballistic arcs, hopping along the surface like bouncing balls, landing, getting energized again, and repeating. There's no wind, no convection, no swirling storms, just a silent ballet of atoms floating in slow motion. The term exosphere usually applies to the outermost fringes of a planet's atmosphere, the very edge where particles start to escape into space. But in the moon's case, the exosphere is all it has. There's no lower atmosphere beneath it. It's just that, an exosphere and bare rock. But this delicate atmosphere isn't just an oddity. It actually changes with time. During the lunar day, when sunlight blasts the surface, some particles are heated and released. At night, they condense or settle. Micrometeorites crashing into the moon also release plumes of gas and dust into the exosphere, temporary little clouds that rise and vanish again. It's dynamic, even if we can't see it with the naked eye. And then there's one of the weirdest things about it. The moon has a sodium tail. Because sodium atoms in the exosphere can be pushed by sunlight via radiation pressure, they're slowly blown off the moon and form a tail that stretches thousands of kilometers into space, pointing away from the sun. For a few nights each month, around the new moon, this sodium tail even passes over Earth. It's invisible to us, but telescopes with the right filters can detect it, a glowing trail of lunar atoms, sweeping across our atmosphere like the wake of a ghost ship. All of this matters more than you might think, because as humans prepare to return to the moon, the exosphere is directly impacted by our presence. Rocket exhaust, landers, rovers, and even footprints can stir up particles, disturbing this fragile balance. Unlike Earth's resilient atmosphere, the moon's exosphere is easily altered. And some scientists worry that we could permanently change it without realizing. That's why future missions, including NASA's Artemis program and upcoming lunar orbiters, include instruments designed to study the exosphere in more detail. Understanding its composition, behavior, and origin can tell us not only about the moon, but about other airless worlds as well, like Mercury, asteroids, and even distant exoplanets. So, while the moon may not have an atmosphere in the way we usually mean it, it does have one in the most extreme, fascinating form possible. An atmosphere made of lunar atoms, fragile chemistry, and forces that stretch out invisibly into space. It's an atmosphere we can't see, can't feel, and can barely detect. But it's there whisper thin, always shifting, and just another way the moon continues to surprise us. A place we thought we understood that turns out, once again, to be not quite what we thought. When we think of dust, we tend to imagine something soft, harmless, maybe even a little annoying, but easy to brush off. But on the moon, dust is something else entirely. It's not just a nuisance. It's not just dirt. It's one of the biggest threats to future lunar missions. So dangerous, in fact, that it can damage equipment, shred spacesuits, and even harm human lungs. The moon's surface is coated in a fine, powdery layer called regolith. At first glance, it looks like dry sand, the kind you might see on a beach, but up close, it's far more alien. Lunar dust isn't shaped by wind or water. There's no atmosphere on the moon to erode or smooth the particles. Instead, it's formed by micrometeorite impacts, which pulverize rock into sharp, jagged shards. Each grain is a tiny, broken blade, angular, rough, and electrostatically charged from constant exposure to solar radiation. When astronauts from the Apollo missions first stepped onto the moon, they were immediately introduced to this problem. The lunar dust clung to everything: boots, gloves, visors, hoses. It wormed its way into seals and joints. No matter how carefully they brushed off before re-entering the lunar module, it got inside. And once it was in, it didn't come out. The dust wore down equipment faster than expected. It scratched visors, jammed zippers, and caused the hinges of spacesuits to grind. Some astronauts reported the smell of gunpowder inside their cabin, a metallic, acrid scent believed to come from the fresh, chemically reactive dust. And since the moon has no atmosphere, the dust isn't weathered or oxidized. It remains chemically aggressive, reacting instantly when it encounters air and moisture. But the equipment wasn't the only thing at risk. Inhaling lunar dust, even trace amounts, could pose a serious health threat. During Apollo 17, astronaut Harrison Schmitt experienced what he called lunar hay fever after breathing in dust that had settled inside the cabin. His sinuses became inflamed, his throat itchy. The symptoms passed, but they raised a serious red flag. If short-term exposure caused irritation, what would long-term exposure do? The concern is that lunar dust, when inhaled, could behave like asbestos. Its microscopic shards could embed in lung tissue, causing inflammation, scarring, or worse, a condition similar to silicosis, a disease miners and construction workers face from breathing in fine silica particles. Once those particles get in, the body has a hard time getting them out. Over time, this could lead to chronic lung damage or even cancer. And because moon dust is so fine, some of it even nano-sized, it's nearly impossible to filter completely. It can float inside spacecraft, on clothing, or get into air systems. On Earth, we have gravity and moisture to pull dust down and keep it from lingering. On the moon, it just stays suspended in the airless environment, clinging to everything. Scientists today take this seriously. NASA has invested heavily in studying lunar regolith, using Apollo samples and synthetic substitutes called lunar simulants. These studies show that moon dust is not only abrasive, but electrostatically charged, meaning it sticks to everything, even defies gravity under the right conditions. During the lunar day, when the surface gets bombarded with solar ultraviolet light, the dust actually levitates slightly above the surface, creating what astronauts called a strange horizon glow just after sunset. Instruments left on the moon have shown signs of degradation over time, likely due to constant exposure to this dust. Solar panels lose efficiency, optical sensors get clouded, moving parts seize. And that's without even considering what happens when humans return for longer stays weeks or months at a time. As space agencies plan future moon missions, dust control is becoming a top engineering challenge. Solutions range from electrostatic brushes that repel particles to self-sealing fabrics to dust docks, entry chambers where astronauts can clean off their suits before entering habitats. The goal is to minimize exposure, both for machinery and for the humans who have to live and work in this environment. Because as harmless as the moon may seem, from 384,400 kilometers away, its surface hides millions of microscopic hazards waiting to infiltrate everything we send. And the very dust that makes those majestic footprints possible is the same dust that could one day destroy the machines we build or hurt the people who use them. The moon may be still, silent, and dead, but its dust is alive with danger sharp, toxic, clingy, and as hostile as anything in deep space. For a place that seems cold, static, and lifeless, The moon has a surprising habit of getting weird, not just geologically weird or chemically weird, but visually weird. For centuries, astronomers have reported strange flashes, glows, and lights coming from the lunar surface. These aren't comets or stars. They're transient, sudden, and very much on the moon itself. They've been documented by amateurs and professionals alike, long before satellites or space stations, and no one, not even NASA, can fully explain them. They're known as transient lunar phenomena, or TLPs. That's the official name, and it's as vague as it sounds, because no one really knows what they are. They appear as brief bursts of light, color, or mist, usually lasting a few seconds to a few minutes. Sometimes they pulse, sometimes they shimmer, sometimes they look like a brief firefly flicker against the harsh gray surface, but they're real. And they've been recorded for over 1,000 years. The first known account goes all the way back to 1065, when monks in Canterbury recorded a glowing object moving across the moon. Over the centuries, more sightings followed. In 1178, 5 monks described seeing the upper horn of the moon split and emit fire, hot coals, and sparks. In 1787, famed astronomer William Herschel wrote of bright lights and apparent volcanoes on the lunar surface. At the time, scientists believed the moon might still be geologically active, possibly even habitable, even into the 20th century. With better optics and telescopes, reports of TLPs persisted. In 1958, Soviet astronomer Nikolai Kozyrev saw a reddish glow near the crater Alphonsus, which he interpreted as a gas emission. His spectrographic data showed the presence of carbon compounds evidence, possibly of a volcanic-like process, but others were skeptical. The moon, by all conventional understanding, was geologically dead, and yet the lights kept coming. In 1963, NASA commissioned a report cataloging 579 credible TLP events spread across multiple observers and decades. Some were photographed, some were recorded with multiple telescopes. The most active locations included craters like Aristarchus, Plato, and Copernicus, all places with unusual geological signatures, strange albedo features, or unexplained thermal readings. What's interesting is that Aristarchus, in particular, is a repeat offender. It's the brightest large crater on the moon, highly reflective, and it seems to glow more than it should. Dozens of TLP events have been linked to that spot alone. Astronomers have described it as flashing, pulsing, or even emitting a faint blue hue. No known Earth-based reflection accounts for it. And it's not just optical illusion spacecraft have picked up real energy emissions from this region. So, what causes these lights? There are a few competing theories. Outgassing the moon may not be completely dead. Some scientists believe that residual gas like radon or argon, trapped beneath the surface from ancient volcanic activity, might occasionally seep out, and when it hits sunlight or reacts with solar particles, it could cause brief luminous clouds or flashes. Electrostatic activity, because the moon lacks an atmosphere. It's constantly bombarded by solar wind. That bombardment can charge dust particles, causing them to levitate and interact with light in unexpected ways. During the lunar sunset or sunrise, these particles might briefly glow or scatter light in eerie flickering patterns. Meteor impacts, small meteoroids strike the moon all the time, hundreds per year. When they hit, they can produce brief flashes of thermal light, which might explain some TLPs, but this wouldn't explain the recurrence of lights in specific craters over decades. Piezoelectric effects. There's also a more exotic idea that moonquakes, which we now know do occur, might cause friction between layers of rock in certain minerals. That friction could, in theory, generate electrical discharges, a kind of moon lightning that flashes out from the surface. None of these theories explain every sighting. Some flashes happen on the dark side, some during times when the moon isn't being impacted or undergoing any seismic activity. And despite decades of observation, we've never seen a TLP happening from orbit in real time with a high-resolution camera. They always seem to dodge our instruments just barely. Still, interest hasn't faded. NASA's Lunar Reconnaissance Orbiter has helped monitor TLP-prone areas with more precision. And private observatories around the world still keep an eye on the moon every night, hoping to catch the next flicker. There are even efforts to set up automated telescopes dedicated solely to monitoring the moon's surface, taking images at millisecond intervals to catch brief flashes. Because here's the thing, the moon is supposed to be dead, airless, emotionless, geologically silent. But these lights, however rare, suggest that something is still happening, some dynamic process we don't yet understand. Maybe minor, maybe subtle, but real. And that uncertainty keeps the mystery alive. Because while the moon has given up many of its secrets, it hasn't given up all of them. Somewhere in those silent craters, in the cracks of a long frozen world, things still move, still flash, for just long enough to remind us the moon is not done surprising us. It's not just a rock in the sky. It's an active mystery, blinking at us literally in the dark. It sounds like something straight out of science fiction. The idea that the moon, our moon, might be hollow, not figuratively, not partially, but literally empty, or at least partially cavernous beneath its rocky shell. To most people, it sounds absurd, even laughable. And yet, this idea has real scientific roots, stemming from seismic experiments, unexpected observations, and a handful of deeply strange anomalies that have refused to go away. Let's start with what's probably the most famous clue. The moon rings like a bell. In 1969, during the Apollo 12 mission, NASA astronauts placed seismic instruments on the moon's surface. Then, once they were safely aboard their module, they deliberately crashed the lunar ascent stage, a piece of discarded spacecraft, back onto the moon to see what would happen. It impacted with the force of about a ton of TNT. The result, the moon vibrated, but not like Earth would. Earth, with its molten core and tectonic damping, quivers and quickly settles. The moon, however, reverberated for over an hour. As one NASA report described it, the moon rang like a bell. Not a literal bell, of course, but the vibrations were prolonged and unusually uniform, as if the energy couldn't dissipate easily. Apollo 13 repeated the experiment, this time unintentionally. After the mission was aborted, the Saturn V rocket booster impacted the moon with even more force. Again, the seismic instruments recorded a deep, sustained echo, lasting 3 hours and 20 minutes. To be clear, no one at NASA said the moon was hollow, but the data raised eyebrows. A solid, homogeneous body shouldn't ring like that. Something was off. The moon's internal structure, it seemed, wasn't behaving the way scientists expected. This led some researchers to theorize that the moon has an unusual composition, perhaps a thin crust, a rigid outer shell, and a less dense interior that allows seismic waves to bounce instead of dissipate. That's not the same as hollow, but it planted the seed for more speculative ideas. And speculation is exactly what followed. In the 1970s, Soviet scientists Mikhail Vasin and Alexander Sherbakov published a provocative paper titled, "Is the Moon the Creation of Intelligence?" They argued that the moon might not be a natural object at all, but an artificial satellite, perhaps even hollowed out by unknown beings and placed in Earth's orbit. Their reasoning: the moon's orbit is too perfect, its composition is odd, its crust is unusually hard, and the ringing bell data suggested internal emptiness. Again, this was not mainstream science, but it didn't go unnoticed. The hollow moon theory quickly caught fire in fringe circles. Some believers claimed the moon was a giant spaceship disguised in rock. Others suggested it was a long-dead alien observation post. Still others speculated that its hollowness could explain the moon's apparent role in stabilizing Earth's rotation, a kind of engineered counterweight. But let's pull it back from the edge for a moment. In modern geology, we know a lot more now than we did in the Apollo era. NASA's Grail mission, the Gravity Recovery and Interior, The laboratory launched in 2011 to map the moon's internal structure with unprecedented detail. It found that the moon's crust is heavily fractured, its mantle is less dense than expected, and there are complex regions deep within, but no hollow core. The data supports a moon that is internally layered, with a small, solid inner core and a partially molten outer core, much like Earth, but less active. Still, the seismic mystery isn't entirely solved. The moon's low seismic attenuation, meaning how poorly it absorbs shock waves, remains one of its most puzzling traits. And that bell-ringing resonance, it still hasn't been fully explained. Some researchers believe the explanation lies in the moon's dry, rigid structure. Without water to help dissipate energy, seismic waves simply travel further. Think of it like striking a bell made of granite instead of bronze. The material matters. Dry rock transmits vibrations much more cleanly than the wet, squishy rock you find on Earth. So maybe the moon rings not because it's hollow, but because it's just bone dry and incredibly stiff. Others point to its low iron content. Unlike Earth, the moon lacks a dense metallic core. That means less gravitational contraction, less internal movement, and more rigid crustal behavior. It also explains why the moon doesn't have a global magnetic field, which would otherwise require a spinning liquid core. But the hollow theory refuses to fully die, partly because it taps into something deeper, a sense of cosmic strangeness. After all, the moon is weirdly perfect. Its diameter is 400 times smaller than the sun's, and it's 400 times closer to Earth. That's why it fits the sun so precisely during an eclipse. It's the only moon in the solar system that does this. Coincidence? Probably, but unsettling nonetheless. And then there's its orbit, almost perfectly circular, tilted, and unusually large for a planetary satellite. No other terrestrial planet has a moon this big in proportion to its host. Some scientists suggest Earth and the moon should be considered a binary planet system, not a planet and a moon. So maybe the moon isn't hollow, but it's definitely strange in shape, strange in composition, strange in behavior. A world that was born in a violent impact somehow became essential to Earth as stability and still confounds scientists with its internal echoes. The hollow moon theory might not hold up under modern data, but its origins, the ringing, the seismic anomalies, the inexplicable patterns are real, and they remind us of something important. We don't understand the moon as well as we think we do. Even now, over 50 years after the first human steps on its surface, the moon still holds mysteries. And some of them echo long, slow, and strange, like something knocking from the inside. For most of human history, we looked at the moon and wondered. Then, in the 1960s and 70s, we visited, and the moon went from mystery to milestone. But lately, something surprising has happened. As the world shifted focus to Mars, China quietly returned to the moon, not just orbiting it, but landing, roving, digging, and bringing samples back. And what they found in the moon soil wasn't just dusty rock. It was something new, something strange, something we've never seen before. Let's start with Change 5. China has a robotic sample return mission that launched in late 2020. It was the first mission to bring back fresh moon rocks in over 44 years. Since the Soviet Luna 24 mission in 1976, Chang'e 5 landed in a previously unexplored region called Mong's Runker, a volcanic dome complex in the Oceanus Procellarum, the ocean of storms. This landing site was chosen deliberately. Unlike the Apollo missions, which mostly explored older lunar terrain, China targeted a much younger surface, believed to be around 1.2 to 2 billion years old, a full billion years younger than the Apollo sites. The goal: to fill in a missing piece of lunar history. What they got was something far more intriguing. Among the samples collected was a completely new mineral, discovered in the lunar soil and identified in 2022. The Chinese team named it changesite, a phosphate mineral that formed in the moon's basaltic lava flows. Structurally, it resembled a type of mineral found in Earth's rare earth-rich regions. But this specific version had never been seen before. Not on the moon, not on Earth. That's already exciting. New minerals mean new insights into how the moon cooled and evolved. But it gets weirder, because embedded in those same samples were traces of helium-3, a rare isotope that barely exists on Earth, but might exist in significant quantities on the moon. Scientists have long theorized that helium-3 deposited by the solar wind and trapped in lunar regolith could be a potential fuel source for nuclear fusion, a kind of clean energy that could power entire civilizations if we ever figure it out. Helium-3 is incredibly rare and expensive here, but the moon's surface, especially its finer dust layers, might hold tons of it. And that's not just theoretical anymore. Change 5 samples confirmed helium-3's presence in measurable quantities, especially in the fine-grained surface material that's been exposed to solar radiation for billions of years. This could make the moon the Saudi Arabia of fusion fuel, a future prize, not just for science, but for geopolitics. But there was something else buried in the data, something stranger. While analyzing the Chang'e 4 mission, the first ever rover to explore the far side of the moon, Chinese scientists detected an unusual gel-like substance in a small crater. The material appeared shiny, viscous, and darker than the surrounding regolith. Instruments showed it had a glass-like structure, possibly formed from high-heat impact processes maybe, the result of a meteorite slamming into the lunar surface and melting rock into an unusual, almost alien form. To be clear, it wasn't alive. It wasn't moving, but it wasn't ordinary. Scientists still aren't sure exactly what it is. Some think it's a kind of impact melt breccia shattered rock fused by heat. Others suggest it could be volcanic glass formed under extreme conditions. Either way, it's unique, and no Apollo mission found anything quite like it. What makes this all so compelling is that the moon was supposed to be done. We thought we'd seen it, sampled it, figured it out. But China, as missions are showing us otherwise, that the moon still has secrets buried, just inches below the surface. And not just scientifically, but industrially, energetically, and maybe even strategically significant ones. The samples are still being analyzed. We've barely scratched the surface literally. Change 5 brought back only 1.7 kilograms of soil and rock. By comparison, Apollo brought back 382 kilograms total, but China's sample is from a completely different region with completely different geology. And that makes it invaluable. It's like turning over a new chapter in a very old book. And they're not done. China is planning Change 6, which will attempt another sample return, this time from the far side of the moon. If successful, it would be the first time any material has ever been brought back from the moon's hidden hemisphere. That region is older, more cratered, and less volcanically active than the near side, meaning the samples could be even stranger, even more alien. So, what's really hiding in the moon soil? New minerals, fusion fuel, melted glass from cosmic impacts, and maybe more we haven't even imagined yet. The moon may look like a dead rock, but under its surface is a time capsule, preserving billions of years of solar system history and holding potential resources that could power our future. Thanks to China's missions, we now know the moon isn't just old. It's diverse, active, and still surprising. And it's reminding us of something we almost forgot, that exploration still matters, that turning over the next stone, even 384,000 kilometers away, can reveal something no one on Earth has ever seen. And all it took was a shovel, a rover, and the curiosity to dig just a little deeper. Imagine walking through a desert, a mountaintop, or an icy field in Antarctica, and bending down to pick up a rock that, unbeknownst to you, came from the moon, not a souvenir from Apollo, not a piece of debris from some secret mission, but a natural moon rock, blasted from the lunar surface by a cosmic impact that flew through space and landed on Earth all on its own. As far-fetched as it sounds, this has actually happened. And it's not just a one-time fluke. Scientists have confirmed that dozens of meteorites found on Earth are lunar in origin. They are natural travelers, ejected from the moon by massive asteroid strikes, surviving a trip through the vacuum of space, and eventually falling to Earth, where they lay unnoticed for thousands, sometimes millions of years. So, how does that work? It starts with an impact something powerful. When a meteoroid slams into the moon's surface at high velocity, the energy released is colossal. The moon has no atmosphere to slow things down, so incoming objects hit hard and fast. That impact can excavate material from the crust and launch it into space. And if that material reaches the escape velocity of the moon, roughly 2.4 kilometers per second, it breaks free of the moon's gravity and begins its journey through the solar system. Most of it just drifts endlessly, captured by the sun's gravitational pull. Some eventually burn up in planetary atmospheres or crash into other objects. But a tiny fraction, a very, very lucky fraction, ends up on a collision course with Earth. Because the moon is relatively close, only 384,400 kilometers away on average, its ejected debris can reach Earth in a matter of days or weeks. And unlike material from further out in the solar system, lunar meteorites don't come in blazing fast. They often enter Earth's atmosphere at lower velocities than typical asteroids, which gives them a better chance of surviving re-entry intact. Once they land, they look just like any other meteorite, dark, dense, scorched from atmospheric entry. For years, scientists had no way of telling where these rocks came from. But then something changed. Starting in the 1980s, with better analytical tools, geologists began to notice that some meteorites had very unusual chemistry. Their isotopic signatures, especially oxygen isotopes, matched samples brought back by the Apollo missions. That was the first major clue. Then came mineral composition, age dating, and trapped gas analysis. Some meteorites had tiny pockets of gas that matched the exact composition of the lunar atmosphere, as measured by instruments on the moon itself. These rocks weren't just similar to moon rocks, they were moon rocks. Today, more than 400 lunar meteorites have been officially identified, found in over 24 countries. Some were discovered in hot deserts, like those in northwest Africa or Oman. Others came from the frozen plains of Antarctica, where meteorites stand out clearly against the ice. That's why Antarctica remains a major hunting ground for space rocks. The cold, stable conditions preserve them for millennia, and the contrast makes them easier to find. And here is the truly amazing part. Some of these natural moon rocks are older than anything the Apollo astronauts ever brought back. While Apollo missions sampled very specific regions of the moon's near side, lunar meteorites come from random parts at the surface, including areas we've never explored directly. They've given us a broader, deeper understanding of lunar geology, insights into parts of the moon that we've never seen up close. They've even raised new questions. For example, one lunar meteorite called Say al-Ahimir 169, found in Oman in 2002, contains an unusual chemical composition that suggests it came from deep within the moon's crust or even the mantle, providing clues to the moon's internal structure, clues we couldn't get from surface samples alone. And then there's the philosophical twist. For centuries, the idea of holding a piece of the moon was pure fantasy, something for poets, dreamers, or science fiction writers. But now we know that pieces of the moon have been falling to Earth all along, unnoticed, scattered across the landscape, waiting for us to recognize them. Think about that. Right now, somewhere on Earth, another piece of the moon might be lying in a desert, or embedded in a glacier, or stuck in the roof of a building after a fireball streaked through the sky. Someone could walk past it, never knowing they were inches away from a 4-billion-year-old rock that had traveled through space, survived atmospheric hellfire, and quietly landed on our planet. It makes the moon feel a little closer, a little more real, not just a distant orb in the sky, but a physical neighbor, one that sometimes shares its bones with us voluntarily, almost gently. A world that leaves fragments behind as souvenirs, as scientific gifts, as reminders that the cosmos is always moving, always exchanging, always dropping hints. So yes, some lunar rocks are here on Earth, and they got here entirely on their own, no rockets, no rovers, just gravity, violence, and time. The moon may seem like it's bathed in endless sunlight, glowing night after night from our point of view on Earth. But if you were standing on the moon, especially near its poles, you'd find a very different reality, a landscape carved by extremes, where light and shadow create zones of eternal brightness and pits of perpetual darkness. And inside those dark places, hidden from the sun for billions of years, lie some of the coldest, most pristine spots in the solar system, and possibly the key to our future on the moon. These places are called permanently shadowed regions, or PSRS. They exist mostly at the moon's north and south poles, where the sun skims the horizon but never rises high overhead. Inside these frozen craters, the temperatures drop to mind-bending lows. NASA's Lunar Reconnaissance Orbiter measured some regions, like the floor of the crater Hermite, at a staggering minus 410 degrees Fahrenheit. That's colder than Pluto. In fact, it's among the coldest temperatures ever recorded in the entire solar system, colder than Mars, colder than Europa, colder even than the surfaces of some comets. So, what's in those shadows? In a word, ice. Not just a little, possibly billions of tons of it. Scientists believe that these PSRS act like natural deep freezes, trapping water molecules delivered by comet impacts, asteroid strikes, or even the slow accumulation of hydrogen and oxygen from solar-wind interactions. Once water finds its way into these eternally dark, airless hollows, it can't escape. There's no atmosphere to help it evaporate, and no sunlight to melt it. It just sits there, frozen, ancient, preserved. NASA has confirmed the presence of water ice in these regions using a combination of data. From the LCROSS mission, which crashed a probe into the moon's south pole in 2009 and detected water vapor in the resulting plume. The Moon Mineralogy Mapper aboard India's Chandrayaan-1 mission, which identified spectral signatures of water ice in shadowed areas. Thermal imaging and neutron detectors aboard orbiters, revealing hydrogen-rich zones that strongly suggest water is locked below the surface. This isn't just a scientific curiosity. It's potentially game-changing for the future of space exploration. Water on the moon means drinking water for astronauts, oxygen for breathable air, hydrogen fuel for rockets, meaning future missions could refuel on the moon instead of carrying all their propellant from Earth. In short, PSRS could become cosmic fueling stations, enabling deeper space travel and long-term lunar bases. That's one reason NASA's Artemis missions are targeting the lunar South Pole. Not because it's pretty, but because those shadows may hold the single most valuable resource off Earth. But exploring them won't be easy. These craters are deep, dark, and deadly cold. Solar-powered rovers can't operate without sunlight. Communications are difficult in the shadowed terrain. Batteries freeze. Equipment becomes brittle. These regions are more alien and more extreme than any place humans have ever visited. Still, plans are in motion. NASA is preparing to send the VIPER Rover Volatiles Investigating Polar Exploration Rover in the coming years. A specialized robotic explorer equipped to enter these shadows and drill into the regolith to test for water content, depth, and composition. If successful, it will mark humanity's first steps into these unlit vaults and into a realm untouched by light since before the age of dinosaurs or even multicellular life. Think about that. These are places that haven't seen sunlight since the moon first cooled, since Earth was a volcanic wasteland, since life was still forming in the oceans. Inside these shadows may be ice older than any glacier on Earth, possibly holding clues about the origin of water in the solar system, and even the molecules that eventually led to life. They are fossilized moments in time, frozen not just in temperature, but in history. So, while the moon looks bright and familiar in our night sky, it holds deep, dark secrets, literal ones, hidden in shadowy craters at the poles, places we've never been, places that may decide the fate of future missions, and places that, paradoxically, might give life, if not to lunar organisms, then to our survival off-world. In a way, the moon still has unlit corners we're only just beginning to understand. Cold, silent, ancient, and full of promise. For thousands of years, people believed that moonlight was cold, not just metaphorically, as in pale or ghostly, but literally. They thought that the light of the moon cooled whatever it touched, that it could spoil food, kill flowers, or even make you sick. Some ancient texts even warned of sleeping under moonlight, suggesting it might cause fevers, blindness, or madness. And here's the strange part. For a long time, people tried to prove it. Let's back up. Today, we know that moonlight is just sunlight reflected off the lunar surface. It's not a separate type of light. It doesn't have any special cooling powers, and it doesn't emit energy. It only reflects a small portion, about 12% of the sun's rays. If anything, moonlight adds a tiny bit of warmth to the night air. Not cold, but before modern physics, light was a mystery. In the ancient world, Aristotle and his followers promoted the idea that celestial bodies influence nature not just gravitationally, but energetically, with the moon controlling moisture, health, and even madness. The term lunatic itself comes from lunar, the Latin word for moon. It was believed that the moon's phases could drive people to fits of insanity. That wasn't a metaphor, it was medical theory for centuries. So, when people observed that the moon was often overhead on cold, dewy nights, especially around the full moon, they made a connection. Moon equals cold. In medieval Europe, this idea became folklore and then pseudoscience. Some physicians claimed that moonlight could rot meat faster or sour milk. Gardeners were advised not to harvest certain herbs at night. Others warned that moonlight could drain vitality from sleeping bodies, especially if it touched the face. Some believed that prolonged exposure caused moonstruck illness, lethargy, confusion, even madness. And this wasn't just superstition. Even during the Enlightenment, scientists and thinkers tried to measure the supposed chill of moonlight. In the 19th century, experiments were performed using thermometers exposed to moonlight, comparing their readings with those kept in shadow. Some claimed to find a small temperature drop, fueling the belief that moonlight had cooling properties. But these results were later shown to be flawed, caused not by the moon's light, but by radiative heat loss from the exposed thermometer to the cold night sky. In other words, it wasn't that moonlight was cooling the thermometer. It was that the surrounding sky was absorbing its heat faster than the shaded one. Real physics entered the picture with modern optics. We now know that moonlight carries only a tiny fraction of the sun energy, about 0.1 lux compared to 100,000 lux for direct sunlight. That's 1/1,000,000th the intensity. It's so weak it can't meaningfully change the temperature of anything it touches. Your skin, your clothes, even ice won't notice a difference under moonlight. Yet the myth lingers. You'll still find fringe theories claiming that moonlight has cooling radiation or that it behaves opposite to sunlight. Some even perform backyard experiments with thermometers, finding not surprisingly that things in moonlight seem colder. But this effect, again, is due to radiative cooling, the loss of infrared heat to the open sky, which has nothing to do with the moon itself. Interestingly, this misconception led to some truly bizarre side paths. In the 1800s, moonlight was blamed for sleepwalking, nightmares, and plant deformities. Even in the 20th century, it featured in fringe medicine and lunar cycle theories about behavior, crime, and fertility. Police departments in some areas once increased patrols on full moons, believing that more crimes occurred under lunar light, a belief not supported by data, but emotionally persistent. It's a testament to how powerful the moon's symbolism is. Its soft glow, shifting face, and connection to tides and time make it feel mystical, influential, and otherworldly. So, when ancient people felt a chill at night and saw the full moon overhead, it made perfect sense emotionally, if not scientifically, to assume the moon was the cause. And in a way, moonlight is cold, not because it cools things, but because of what it represents. It's the light of reflection, not fire. The glow of silence, not heat. It evokes frost, stillness, and quiet. But the science says otherwise. Moonlight is neutral, gentle, inert. It's a mirror of sunlight filtered through gray dust, scattered across space. It doesn't burn, and it doesn't chill. But for millennia, we thought it did. And that little mistake shaped everything from superstition to science. So the next time you stand under a full moon and feel the night air cool against your skin, remember, the moon isn't doing that. The universe is. But if it feels like the moon is to blame, well, you're in good company. So did everyone else for about 2,000 years. The moon is 384,000 kilometers away. Getting there took the most advanced technology of the 20th century, the coordination of hundreds of thousands of people and billions of dollars. So when pieces of the moon were finally brought back to Earth, real physical samples of another world, they were treated like sacred relics, scientific treasures, and priceless history. And yet, one of them ended up in a garage, forgotten, misplaced, missing for decades. This isn't a movie plot. It actually happened. To understand the full strangeness of this story, we need to go back to the early 1970s, when the United States, fresh off the success of the Apollo missions, decided to share its lunar bounty with the world. President Richard Nixon's administration created the Goodwill Moon Rocks program, where small fragments of lunar rock were mounted on plaques and gifted to 135 countries and all 50 U.S. states. These samples were tiny, just a few grams each, but they were the real thing. Slices of moon rock from missions like Apollo 11 and Apollo 17, embedded in clear acrylic globes, mounted alongside national flags flown to the moon. It was a gesture of diplomacy, unity, and scientific pride. But here's where things get weird. Over the years, many of these Goodwill moon rocks simply disappeared, lost, stolen, misplaced. Some were auctioned off on the black market for millions. Others vanished into private collections. A few were thought to be destroyed in fires, floods, or wars. The exact number missing is still unknown, but it's estimated that more than half of them are unaccounted for. Which brings us to the case of the missing moon rock from Honduras. This particular sample came from Apollo 17, the final Apollo mission. In the 1970s, it was given to the government of Honduras as a diplomatic gift. But somewhere along the line, it vanished, not lost in a government archive or museum, but into the hands of a private collector. Joseph Guthines, a former NASA special agent turned moon rock sleuth, began tracking these missing artifacts in the 1990s. Guthines launched a sting operation known as Operation Lunar Eclipse, posing as a wealthy buyer interested in purchasing moon rocks. Through a chain of fake companies and email aliases, he traced the Honduras rock to a man in Florida who had gotten it unbelievably from a former U.S. diplomat who'd held on to it as a keepsake. For years, it had sat in a garage, boxed away like an old trophy, covered in dust, a piece of another world, misplaced like forgotten holiday decorations. When authorities finally retrieved it, they confirmed it was genuine, an actual lunar basalt fragment collected by Apollo 17 astronauts Eugene Cernan and Harrison Schmitt in 1972. Its journey had taken it from the Torres Nitro Valley on the moon to a handshake photo op with a Honduran president to a storage box in suburban America. And this isn't an isolated case. Moon rocks have turned up in some of the strangest places. One was found in a museum drawer, mislabeled as a random stone. Another surfaced in a diplomatic estate sale. Several were discovered missing from government buildings after regime changes or political upheaval. In fact, the sheer rarity and value of lunar samples has made them a kind of space-age currency in the world of black market memorabilia. A single gram of moon rock can be worth upwards of $5 million, depending on provenance. And because NASA strictly prohibits private ownership of lunar material collected during Apollo, any such rock that ends up in civilian hands is technically illegal to possess. That hasn't stopped collectors from trying. There are active investigations, international recovery efforts, and even an unofficial moon rock recovery team, largely volunteers and scientists, who scour old records to track down missing samples. So, why does this matter? Because these rocks are more than souvenirs. They're scientific time capsules, carrying clues about the moon's history, Earth's formation, and even the early solar system. Losing one isn't just embarrassing, it's a genuine setback for science. Each piece of moon rock is irreplaceable. We only have about 382 kilograms total from all Apollo missions. Compare that to the tons of Martian meteorites found on Earth, or the regular supply of asteroid material we now receive via robotic missions. Moon rocks are finite, fragile, and historically priceless. The Garage Find and others like it are reminders of how even the most extraordinary things can become ordinary if we're not careful. Something that once traveled across space, collected by astronauts wearing million-dollar suits, can sit unloved next to lawnmowers and toolboxes. It also tells us something about how time changes perspective. What was once the greatest achievement in human history slowly faded from public memory until someone remembered to open the box. And in that box, a rock. Just a rock. Except it wasn't. It was the moon. When we think of the moon's surface, we picture a dusty, cratered wasteland, flat, barren, colorless. But look closer, really look, and you'll find mountain ranges, towering peaks, and rugged highlands that rival anything here on Earth. In fact, some of the moon's mountains are taller than the Rocky Mountains, rising from the ancient crust like scars from a time when the solar system was still violent and young. Let's start with the basics. The moon has no tectonic plates, no volcanoes, not anymore, no erosion by wind or rain. So, how exactly does it have mountains? The answer lies in impact. Unlike Earth, where most mountains are formed by tectonic activity plates colliding and uplifting rock, the moon's mountains were born from cosmic violence. Billions of years ago, massive asteroids and protoplanets slammed into the lunar surface with unimaginable force. These collisions carved out enormous basins, and the leftover shock waves pushed up mountainous rims around them. Think of dropping a stone into soft clay. The splash rises, freezes, and becomes a jagged edge. One of the most dramatic examples is the Montes Runker, a dome-shaped mountain massif in the moon's northwest. But even more impressive is Montes Apenninus, a rugged range that borders the Imbrium Basin, one of the largest and oldest impact craters on the moon. Another giant, Mons Huygens, considered the tallest mountain on the moon, reaches up to 5.5 kilometers, 18,000 feet, taller than Mount Rainier, Mount Whitney, or any mountain in the lower 48 states. Mons Huygens towers over the surrounding plains like a frozen wave, the remnant of a collision that shook the moon's crust to its core. Then there's Mons Hadley, located near the landing site of Apollo 15. This stunning peak rises about 4.5 kilometers, 15,000 feet, above the surrounding terrain. When astronauts David Scott and James Irwin landed nearby, they described it as absolutely breathtaking, a vertical wall of gray rock that loomed in the lunar sky like a distant fortress. But here's the thing. Even though the moon's mountains are tall, they don't feel quite as tall when you're standing on the surface. Why? Two reasons. First, the moon's lack of atmosphere means there's no haze, no clouds, no gradual fading of distance. Everything looks crystal clear, no matter how far away it is. That makes even enormous mountains look oddly close. It flattens your sense of depth, making scale hard to judge. Second, the moon's gravity is only 1/6 of Earth's. So, while a mountain may look like a dramatic peak from orbit, climbing it would feel much less intense than doing the same on Earth. There's less gravitational resistance, no altitude sickness, no oxygen loss, and no need to fight Earth's pull. You'd be bouncing your way uphill, not trudging. And yet, these mountains are more than just relics. They're geological museums, preserving material from the early moon, unmixed and untouched by erosion. Some of the rocks at higher elevations are 4 billion years old, part of the original lunar crust. Studying them could help scientists understand how the moon formed, and by extension, how Earth itself came to be. In fact, future missions, robotic and human, are being planned specifically to explore these highlands, not just for science, but for potential resources. Some mountain regions receive nearly constant sunlight, making them ideal for solar-powered infrastructure. Others may contain exposed minerals, oxygen-rich regolith, or even access to hidden ice deposits nearby. So yes, the moon has mountains, and not small ones either. These are colossal structures, born from cataclysm, frozen in place for billions of years. Mountains that dwarf the imagination, that once towered above Apollo astronauts, that may one day serve as outposts, observatories, or launch points for journeys even farther into space. We often think of the moon as still, passive, but its mountains tell a different story of fire, force, and impact, of a world shaped not by gentle flows, but by celestial violence. The scars are still there, so are the heights. And one day, we may climb them. When you look up at the moon on a clear night, you'll notice dark patches spread across its face. Broad, smooth plains that contrast with the lighter, cratered highlands. They form the familiar man in the moon pattern, or the rabbit, or whatever shape your culture sees. But those shadowy regions aren't just tricks of the eye. They're real geological features. Vast, ancient lava seas called Maria, pronounced Maria. The word comes from the Latin for seas, because early astronomers, gazing through primitive telescopes in the 1600s, thought these dark zones were bodies of water. It wasn't until centuries later that we realized they're actually basaltic plains, formed by massive volcanic eruptions billions of years ago. And they tell a story of a moon far more violent and molten than it looks today. Most of the moon's surface is made of highlands, rugged, mountainous, heavily cratered terrain that reflects more sunlight and looks brighter from Earth. But Maria make up about 16% of the surface, concentrated mostly on the side that faces us. These areas are smoother, lower, and much darker, made of basalt, the same kind of rock that forms ocean floors and volcanic islands on Earth. So, how did they get there? It all started with impact events, unimaginably huge ones. Between 3 and 4 billion years ago, the moon was pummeled by asteroids and protoplanets during what's known as the Late Heavy Bombardment. These impacts carved out immense basins, some stretching hundreds of kilometers wide. The force was so great that it fractured the lunar crust, creating channels that allowed magma from the interior to erupt onto the surface. And then came the floods, not of water, but of fire. Lava poured out from deep fissures, spreading across the impact basins in thick, slow-moving sheets, filling them in like syrup in a bowl. Over time, the lava cooled and solidified into smooth basalt plains. These became the Maria, still black seas of frozen lava, scarred by time, but eerily flat compared to the jumbled terrain around them. We've given these Maria poetic names, remnants of an older, more romantic era of astronomy. Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed. Mare Imbrium, the Sea of Rains, one of the largest impact basins in the solar system. Mare Serenitatis, the Sea of Serenity; Mare Crisium, the Sea of Crisis; Oceanus Procellarum, the Ocean of Storms, the largest of them all. Despite their names, these seas have never held water. They're dry, solid, and cold. But they were once geologically alive, glowing rivers of molten rock that reshaped the moon's face. And unlike Earth, which recycles its crust through plate tectonics, the moon's lava seas have been frozen in place for billions of years. What you see when you look up is a map of ancient volcanic violence, unaltered and preserved. The basalt in the Maria is different from the rocks in the highlands. It's denser, darker, and richer in iron and titanium, which is why it reflects less sunlight. Some regions are even glassy, the result of lava cooling so quickly it didn't have time to form crystals. That glass can sometimes be seen in Apollo rock samples, shimmering under microscopes like the moon's own obsidian. And then there is a strange symmetry. Most Maria are on the near side of the moon, the side that always faces Earth. The far side, while just as cratered, has almost no Maria at all. Why? Scientists aren't entirely sure. It could be due to thinner crust on the near side, allowing more magma to break through. Or it might be related to the internal distribution of radioactive elements, which produced localized heating beneath the crust. Either way, this lopsided lava flow has left the moon with a two-faced appearance: a smooth, familiar side and a rugged, hidden one. Today, the Maria are among the flattest places in the solar system. That's why they were chosen as landing sites for Apollo missions. Easy to land on, relatively safe, and rich with volcanic history. The astronauts who walked on these plains were literally treading on the moon's cooled blood, the last signs of a molten heart that has long since gone quiet. But the Maria may still have more to offer. Some scientists believe they hold trapped gases, volatile minerals, or even traces of water in the form of bound hydroxyls. Others are studying them to understand how planetary bodies lose heat, how magma behaves in low gravity, and how crusts form and fracture in the absence of tectonic movement. So, those dark splotches on the moon, they're not decoration. They're not illusions. They're cosmic scars, frozen oceans of fire, the leftovers of a moon that once roared with internal heat and was reshaped by violence on a planetary scale. Next time you look up and trace the patterns on the moon's face, the smile, the eyes, the shadows, remember that those aren't just shapes. They're lava seas, older than any mountain on Earth, and they've been staring back at us for billions of years. We've sent men to the moon, left flags in the dust, and returned with priceless rock samples. But one of the most quietly brilliant things NASA left behind, and one of the few that has still doing its job today, is something you've probably never thought about: retroreflectors. They don't look impressive, no solar panels, no antennas, no flashing lights, just small panels of mirrored prisms, about the size of a suitcase, sitting silently on the lunar surface. Yet these retroreflectors are part of the longest-running experiment in the history of space exploration. They've been quietly bouncing laser beams back to Earth since 1969, and they're still doing it right now. So, what exactly is a retroreflector? It is a device made of corner cube prisms, usually 3 mirrors arranged at right angles, that reflects light straight back toward its source, no matter what angle it hits from. It's like the reflective coating on road signs or bike reflectors, but supercharged for space. NASA installed retroreflectors on the moon during Apollo 11, Apollo 14, and Apollo 15 missions. The Soviet Union also sent 2 aerobatic lunar missions. Altogether, 5 retroreflectors were placed on the lunar surface between 1969 and 1973. Their purpose: to measure the distance between the Earth and the moon with incredible precision down to the millimeter. Here's how it works. Scientists on Earth aim an ultra-powerful laser at one of these retroreflectors. The beam travels through the atmosphere, across space, and hits the moon. The retroreflector bounces the light back, and extremely sensitive detectors measure the time it takes for the pulse to make the round trip about 2.5 seconds total. Multiply that time by the speed of light, divide by 2, and you get the exact distance to the moon. Every single day, we do this. And every single day, those little mirrored boxes sitting in silence on a dead world answer back. Thanks to this experiment, called lunar laser ranging, we've learned things that would be impossible otherwise. The moon is moving away from Earth at about 3.8 centimeters per year, which may not sound like much, but over millions of years, it adds up. And yes, it's slowly lengthening our days on Earth. We've been able to test Einstein's theory of general relativity by measuring how the Earth-Moon distance is affected by gravity, motion, and time dilation. So far, Einstein is still holding up. We've refined our understanding of the moon's orbit, Earth's wobble, and even tiny shifts in the moon's rotation, all critical for navigation, climate models, and long-term planetary science. And here is what makes it even more impressive. The reflectors still work perfectly after more than 50 years in space. They've survived extreme temperature swings from plus 250 degrees Fahrenheit to minus 280 degrees Fahrenheit every lunar day. They've endured constant micrometeorite impacts, radiation, and dust accumulation. And yet, when scientists aim lasers at them from observatories in Texas, France, and elsewhere, the signal still comes back. It's not easy. The laser pulse spreads out as it travels, and by the time it reaches the moon, it's about 2 kilometers wide. When it bounces back, only a handful of photons make it to the detector, maybe 1 photon per second. Catching that return signal requires incredible precision, timing, and patience. But it works, and not just as a scientific tool. These reflectors have become a symbol of enduring design proof that a small, simple object can outlast almost everything else we've sent into space. The Apollo landers are silent. The flags are bleached white by radiation. The astronauts are long gone, but the retroreflectors are still answering the call. In recent years, scientists have noticed that the reflectors are not quite as efficient as they used to be, probably due to lunar dust kicked up by micrometeorites or thermal cycling. This has sparked interest in sending new reflectors, using improved materials that resist dust and heat better. Upcoming missions, including NASA's Artemis program and private lunar landers, plan to deliver new retroreflectors to fresh locations, creating a more distributed network across the moon's surface. Why? Because this simple, elegant experiment still has more to teach us. It can help pinpoint moonquakes, monitor gravitational shifts, and even support GPS-like systems for future lunar explorers. Think about it. A quiet mirror, sitting untouched on a cratered plain, still talking to us through light, still sending whispers of data across the vacuum of space. No power, no moving parts, just geometry and the physics, perfectly executed. It is one of the most beautiful things we've ever done in science, leaving behind a tiny object on another world and giving it a job so pure and precise that it is still fulfilling its mission half a century later. So next time you look up at the moon, remember it's not just reflecting sunlight. Somewhere up there, a little patch of human ingenuity is reflecting laser light too quietly, reliably, faithfully, still saying, "I'm here." As silent and desolate as the moon may seem, it's not a free-for-all. You can't just fly there, plant a flag, and claim it as your own. That might work in a sci-fi movie or a game of Risk, but in the real world, the moon has something incredibly human applied to it. A legal framework. A literal space treaty forged by world governments to make sure that our nearest celestial neighbor remains, at least in theory, a place of peace. The idea that we'd need laws about the moon might sound strange, especially since only a handful of humans have ever set foot on it. But as early as the 1950s, when space travel began to shift from fantasy to possibility, world leaders realized something important. Space could become the next battlefield unless they made rules to prevent it. So, in 1967, the Outer Space Treaty was born. Its full name is the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other celestial bodies. A mouthful, but also one of the most historic agreements in international law. It was drafted during the Cold War, when the US and the Soviet Union were locked in a race for space supremacy. And yet, both sides agreed the Moon should not become a new front in global conflict. Signed initially by the United States, the Soviet Union, and the United Kingdom, and later joined by over 110 countries. The Outer Space Treaty sets some very clear boundaries. No nation can claim sovereignty over the Moon. Planting a flag doesn't make it yours. The Moon and all celestial bodies must be used exclusively for peaceful purposes. Weapons of mass destruction are strictly prohibited in orbit or on the Moon. Activities on the Moon must be conducted with international cooperation and transparency. States are responsible for all space activities, whether carried out by governments or private companies. If a spacecraft or astronaut is in distress, other nations must assist, even if they're enemies on Earth. In short, the Moon belongs to no one and to everyone. But that idealistic vision has become increasingly complicated. In 1979, a follow-up treaty was introduced, the Moon Agreement, which aimed to expand on the Outer Space Treaty and treat lunar resources as the common heritage of mankind. It proposed a system for sharing the Moon's benefits, including any future mining or commercial exploitation, with all countries, especially developing ones. But here's the catch. Almost no major spacefaring nation signed it. The United States, Russia, and China all opted out. As of now, only 18 countries have ratified the Moon Agreement, none of which have space programs capable of launching crewed missions. Why the resistance? Because space got commercial. Companies like SpaceX, Blue Origin, and others want to mine the Moon's ice, harvest its minerals, and build infrastructure. The idea of treating the Moon as a shared inheritance didn't sit well with governments or corporations hoping to stake claims. And so, in practice, the Outer Space Treaty is the only widely accepted law governing the Moon. And it's full of gray areas. For example, it forbids owning land, but doesn't clearly regulate resource extraction. It bans military use, but what about defensive infrastructure or surveillance satellites? It calls for cooperation, but what happens if two countries try to mine the same crater? Recognizing these gaps, the U.S. introduced the Artemis Accords in 2020, a non-binding set of principles for responsible Moon exploration. Countries that sign the accords agree to share scientific data, preserve heritage sites like Apollo landing spots, and avoid conflict over resources. As of now, more than 40 countries have joined, but key players like Russia and China have not. So, we now have a strange legal landscape. The Moon is governed by treaties written before cell phones existed, enforced by a mix of voluntary agreements and mutual goodwill, while a new space race begins this time, not for flags, but for water, minerals, and power. And this matters more than ever. The Moon is becoming a hub again. NASA plans to return humans to the lunar surface this decade. China has its own ambitious missions, including a potential base at the South Pole. Private companies are planning landers, drills, even habitats. And all of them are heading for the same high-value spots, like shadowed craters filled with ice or sunlit ridges perfect for solar power. What happens when two crews arrive at the same resource? Who decides who gets to stay? Who owns what's extracted? And what rules will guide that process? Right now, the answer is, we don't know. The treaties we have reflect the values of another era, hopeful, cautious, idealistic. They never imagined a world where billionaires would send rockets to the Moon, or where nations would talk about lunar mining rights. Yet they're still the foundation of space law today. So yes, The moon has an official peace treaty, several, in fact, and they've kept the moon free from weapons, borders, and conflict for over 50 years. But the next 50? That's where things get tricky, because the moon may not belong to anyone, but soon everyone will want a piece of it. When you look up at the moon full glowing, perfect, it seems like the very definition of a smooth, round celestial body, a cosmic pearl. But that's an illusion. In reality, the moon isn't perfectly spherical at all. It's lopsided, bulging, and asymmetrical, shaped not just by gravity, but by deep, ancient forces that have left it slightly deformed and permanently off balance. Let's break that down. The moon, like most planetary bodies, is roughly spherical because of gravity. Over time, any large object's own mass pulls it into a rounded shape, but round in astronomy is rarely perfect. Earth, for example, is slightly flattened at the poles and bulges at the equator due to its rotation. The moon doesn't rotate fast enough for that kind of equatorial bulge, but it has its own weirdness. The most striking thing, the moon's mass is not evenly distributed. Its center of mass is offset by about 2 kilometers toward Earth. That means the moon is essentially heavier on one side, the side facing us. This imbalance isn't visible from Earth, but it has profound consequences. It's part of the reason we always see the same side of the moon, the near side, rather than a rotating panorama. The moon is tidally locked, and its lopsided mass makes it more stable in that locked orientation, like a spinning coin that settles on its heavy side. Even stranger, the moon's crust is thinner on the side facing Earth than it is on the far side. On average, the near side crust is about 20 kilometers thinner, and it has far more lava plains, volcanic activity, and radioactive elements like uranium and thorium than the far side. That's why the familiar face of the moon looks dark and patterned. Those are ancient lava basins, while the far side is much rougher, brighter, and more cratered. Why this asymmetry exists is still a mystery, but scientists have some theories. One idea is that, early in the moon's history, Earth's heat influenced how the moon cooled. When the moon first formed, likely from a giant impact, it was molten, a glowing ball of magma. The side facing Earth would have been constantly bathed in radiant heat, while the far side cooled more rapidly. This uneven cooling could have caused differences in crust thickness and interior composition, locking in a permanent imbalance. Another theory suggests the moon might have once had a companion, a second, smaller moon that eventually collided with it. If so, the impact might have smeared extra material onto one side of the moon, permanently reshaping its outer layers and creating the lopsided structure we see today. Whatever the cause, the result is measurable and weird. NASA missions have detected gravitational anomalies on the moon that match this uneven distribution of mass. Some of these are maskins, short for mass concentrations regions, were buried. Dense material pulls harder on orbiting spacecraft. Apollo missions had to adjust their flight paths to avoid being subtly tugged off course. Lunar orbiters still account for this today. In simple terms, parts of the moon's gravity are stronger than they should be because of buried structures beneath the surface that throw the balance off. And let's not forget the shape itself. If you could somehow drain away all the craters and mountains and look at the moon as a smooth object, it would still be a little squashed, slightly elongated in the direction facing Earth. Think of it like a water balloon tugged gently toward our planet, pulled by tidal forces. That elongation isn't dramatic, just a few kilometers difference, but it's real. And over billions of years, the moon has held on to that stretched shape, even as it slowly drifted farther away. So, while the moon may look like a serene, polished sphere in our night sky, its real geometry is far from perfect. It's a world with a lumpy gravitational field, a thinner volcanic near side, a thicker battered far side, and a core offset slightly from center. In other words, a cosmic imbalance frozen in stone. This lopsidedness might seem like a minor quirk, but it's helped shape how the moon evolved, how it orbits, how it interacts with Earth, and how we plan future missions. Understanding the moon's strange structure helps scientists learn about planetary formation, tidal mechanics, and even the ancient history of our own planet. So the next time you gaze up and see that perfect glowing disk, remember, it's a lie of light. The moon isn't symmetrical. It isn't even centered. It's been stretched, smashed, and pulled into a shape that tells a story one written in gravity, lava, and time. It may look like a pearl, but underneath, it's a twisted, off-center relic of cosmic violence. And it's still turning that same strange face toward us, always. When we think of the moon, we think sterile, airless, lifeless, a frozen vacuum bathed in solar radiation where no known organism could survive. It's the ultimate definition of a dead world. And yet, there's a lingering question that scientists can't fully answer. Did we accidentally bring life there? Because, during the Apollo missions, despite rigorous precautions, there's strong reason to believe that Earth microbes may have hitched a ride to the moon. And in at least one case, they might have survived. Let's go back to 1967, 2 years before Apollo 11. NASA was racing to land humans on the moon, and no one yet knew whether it harbored microbial life. If astronauts brought moon dust back to Earth, could it carry alien pathogens? Could it contaminate our planet's biosphere? These were real concerns, serious enough that the early Apollo astronauts were quarantined for weeks after returning home. But what if the contamination worked in the opposite direction? Consider Surveyor 3, a robotic spacecraft that landed on the moon in 1967. It was an unmanned probe designed to test lunar soil before humans ever set foot there. Fast forward to 1969. Apollo 12 astronauts Charles Pete Conrad and Alan Bean landed just 183 meters away from that old Surveyor. In one of the most ambitious and scientifically clever moments of the mission, they hiked over to the aging spacecraft, took pictures, removed parts of it, including a TV camera and circuit board, and brought them back to Earth. Why? To study what happens to equipment after years on the moon. But when those parts were analyzed in a clean lab at the Johnson Space Center, researchers made a shocking discovery. A colony of live bacteria had somehow survived. The organism was Streptococcus mitis, a common microbe found in the human mouth and respiratory tract. It had supposedly endured 2 years of lunar vacuum, radiation, and temperature extremes, and it was still alive. The news made headlines. Scientists were stunned. How could a microbe, one that can't even survive mild desiccation on Earth, last 2 years in space? Did it somehow enter a dormant state and reawaken in the lab? For years, that claim stood as a potential case of accidental panspermia, with humanity having seeded life on the moon without even realizing it. But here's where things get complicated. In the decades since, many scientists have cast serious doubt on that finding. The Surveyor parts were not opened in a sterile vacuum. They were brought back to Earth, handled by humans, and may have been contaminated during retrieval. The lab wasn't perfectly sealed. Some now believe that the bacteria were reintroduced after the hardware got home, not survivors from the lunar surface, but stowaways from a lab coat or an exhale. Still, the case has never been fully resolved. And even if those bacteria didn't survive on the moon, others might have. You see, sterilization wasn't perfect in the Apollo era. NASA tried spacecraft were baked, scrubbed, and vacuum treated. But even with the best methods available at the time, there's a very real chance that some Earth microbes made it onto the lunar surface inside camera housings, flagpoles, hatch seals, or even the spacesuits themselves. Bacteria are remarkably resilient. Some can survive in dormant spore form for years, shielded from radiation by layers of dust, metal, or plastic. And there are areas on the moon like deep lava tubes, shaded craters, or buried regolith, where conditions might be just stable enough for spores to survive longer than we think. Today, we know much more about how tough microbes can be. Experiments aboard the International Space Station have shown that certain bacteria and tardigrades can survive exposure to space extreme cold, radiation, vacuum, if protected even slightly. The European Space Agency's EXPOSE missions have kept microbial colonies alive outside the ISS for months. Some microbes literally shut down their metabolism, go dormant, and wake up later, good as new. So, is it possible that some microbial fingerprints from Apollo are still clinging to the moon's surface? Yes. In fact, one of the big concerns for modern lunar science is forward contamination, the accidental transfer of Earth life to other worlds. NASA and other agencies now follow strict planetary protection protocols for missions to Mars, Europa, Enceladus, and even the Moon, depending on the region. Any place that might harbor water or support life, even in theory, must be approached with extreme caution. Because once Earth microbes are there, you can't undo it. There's even a philosophical wrinkle. If we find life on another world, how do we prove it's alien and not just something we brought with us? As space exploration ramps up again with Artemis SpaceX landers and international lunar bases on the horizon, these questions are getting louder. Do we need to clean up the moon? Can we preserve its pristine environment? Or has the biological bell already been rung, with Apollo's bacteria riding into history and possibly still lingering in the dust? So yes, some Apollo missions may have brought microbes to the moon. Maybe they survived, maybe they didn't. But the fact that we even asking that question proves something remarkable. The moon isn't just a rock. It's a stage, and we've been leaving more behind than just footprints. When we talk about the moon, it's easy to assume we've been there, done that. After all, humans landed 6 times, sent back rock samples, left rovers and flags, and have studied it for decades. We know what it looks like. We've mapped it. We've orbited it. There's nothing left to see, right? Not even close. The truth is, we've only explored a tiny fraction of the moon's surface, and most of it has never been touched, tested, or truly understood. In fact, if you added up all the areas that human boots or rovers have visited, it would be less than the size of a small city. Let's break that down. The moon's surface area is about 38 million square kilometers, roughly the size of Africa. It's massive. And yet, between 1969 and 1972, the Apollo astronauts explored a total of just 93 square kilometers on foot and in lunar rovers. All 6 landing sites were confined to the equatorial region of the near side, mostly chosen for their relative flatness and safety for landings. Apollo 11 stayed within a few hundred meters of the lunar module. Apollo 12 ventured slightly farther to explore the Surveyor 3 probe. Apollo 15, 16, and 17 had rovers, allowing them to cover more ground. But even the longest lunar drive was only about 35 kilometers. That's it. That's the total of human exploration on the moon. And robotic missions? While there have been more of them from the US, Soviet Union, China, India, and others, they're still limited. Soviet Lunokhod rovers covered a few dozen kilometers. China's Chang'e 3 and Chang'e 4 landed on the near side and far side, respectively, and explored small patches with their U-2 rovers. India's Chandrayaan 3 made a soft landing in 2023 near the moon's south pole, but again, traveled only a short distance. Even if you include all landers, orbiters, and sample return missions, the amount of the moon that has been physically visited and tested is laughably small. Over 99.99% of the lunar surface remains unvisited, untouched by humans or robots. Why does that matter? Because the moon is not uniform. It's not just gray rock repeated endlessly. Its surface varies wildly in composition, geology, age, and potential resources. There are ancient volcanic domes, jagged riles that look like collapsed lava tubes, enormous impact basins buried under debris, Areas rich in rare earth elements, helium-3, or even frozen water. We've barely scratched the surface of any of these. Consider the South Pole of the Moon, one of the most scientifically intriguing regions. There are deep, permanently shadowed craters that may hold billions of tons of water ice, possibly left by comets or locked in for billions of years. This area is also a prime target for future bases because it offers both sunlight for power and ice for fuel. Yet, we've never been there in person, not once, not even close. Or take the far side, the hemisphere that never faces Earth. It wasn't photographed until 1959, and to this day, only one mission has landed there. China's Chang'e 4 in 2019. It revealed an entirely different landscape, thicker crust, fewer lava seas, and mysteries about the moon's internal composition that challenge our current models. And what about underground? There's growing evidence of massive lava tubes, some potentially large enough to house a city that have never been explored. No one knows what they hold: ancient water, preserved geology, natural shelter for future astronauts. We won't know until we go. Despite all our confidence and technology, the moon remains a poorly explored frontier. Most of what we know comes from orbital imagery, remote sensing, and a few dozen kilograms of rock samples. And while those samples are incredibly valuable, they all came from just 9 locations, and mostly from similar terrain. Entire regions, highlands, basins, volcanic plains, magnetic anomalies have never been sampled directly. In fact, when new lunar meteorites are found on Earth, they often contain minerals and compositions that have never been seen in Apollo samples, suggesting that the moon is more geologically diverse than we ever imagined. So why haven't we explored more? For decades, the moon took a backseat to other missions: Mars rovers, deep space telescopes, asteroid landings. The been there, done that mentality made funding lunar exploration hard to justify, but that's finally changing. NASA's Artemis program, China's lunar plans, and the rise of commercial space companies have reopened the moon as a major target. Artemis 3 aims to send humans to the South Pole, possibly in the next few years. Multiple robotic missions are scouting potential landing and mining sites, and private landers are preparing to deliver scientific payloads, infrastructure, and resource prospectors to untouched regions. The goal? To explore, not just symbolically, but systematically. Because the moon isn't just a rock. It's a record, a museum of the solar system's early history, a stepping stone to Mars, a natural laboratory for science, and a place that might hold resources critical to humanity's future in space. We've stared at it for tens of thousands of years. We visited a few corners, but in truth, we've barely begun. The moon is often thought of as a pristine, untouched world, silent, ancient, and unspoiled. But if you were to walk across certain parts of its surface, especially near the Apollo landing sites, you'd find something surprisingly familiar: litter. Lots of it. Not candy wrappers or soda cans, but a different kind of trash, one left behind by science, exploration, and the raw logistics of getting off the surface alive. Because, as it turns out, humanity has left over 400,000 pounds, more than 180,000 kilograms of debris on the moon. That's right, nearly 200 tons of stuff sitting there in the dust, and much of it isn't glamorous. Some of it was left on purpose. Some of it was abandoned out of necessity. And some of it is there simply because bringing it back was never part of the plan. Let's start with the basics. Every Apollo mission that landed on the moon had one major problem: weight. The heavier the payload, the harder and more expensive it was to launch from Earth. That problem got even worse on the way back, when astronauts had to lift off from the moon's surface in the ascent stage of the lunar module. They had to shed as much mass as possible to escape the moon's gravity and rejoin the command module in orbit. So, how did they do that? They left things behind, a lot of things. Each Apollo landing resulted in the abandonment of the descent stage of the lunar module, the big gold-legged platform that served as a launch pad, scientific equipment no longer in use. Cameras and film canisters, empty fuel containers, tools, EVA extravehicular activity gear, experiments that were deployed and later left behind, rover parts. And in the case of Apollo 15, 16, and 17, the entire lunar roving vehicle. But it goes further than that. Astronauts also jettisoned things like boots, backpacks, hammers, antennas, and even urine collection containers. Yes, bodily waste was dumped too. In fact, there are nearly 100 sealed bags of human waste left on the moon: feces, urine, and vomit bags from various missions, all carefully stored in the belief that every ounce mattered when launching back into lunar orbit. And the trash wasn't just from the Apollo program. Over the years, the moon has been the target of dozens of robotic missions from multiple countries, including the US, the Soviet Union, China, India, Japan, and the European Space Agency. Many of these spacecraft crashed intentionally, serving as impact experiments or simply running out of fuel and being guided into controlled descents. Others were soft landers that left rovers or stationary instruments behind. The result: a lunar surface dotted with defunct orbiters, impact stages, crash debris, rover wheel tracks, broken probes, solar panels, antennas, shattered lenses. Even things like golf balls. Alan Shepard hit 2 with a modified 6-iron on Apollo 14 and a sculpture, a tiny aluminum memorial to fallen astronauts and cosmonauts left during Apollo 15, remain among the lunar litter. The total known inventory includes over 800 separate objects, ranging from massive spacecraft parts to tiny bolts and wires. And many of them are still exactly where they landed, undisturbed for decades. There's no wind or weather on the moon to sweep them away, no bacteria to break them down, no plants to cover them up. In fact, some scientists believe the Apollo site's trash and all should be considered historical landmarks. They've proposed protecting them as cultural heritage zones like ancient ruins, because they're not just piles of junk. They're evidence of one of humanity's greatest achievements. But others see something more complicated. As we plan future missions with NASA's Artemis program, commercial landers, and international bases, the question of what to do with the moon's trash becomes urgent. Should we clean it up, recycle it, leave it as is, use it to build something new? Some engineers have proposed repurposing old equipment using metal from defunct landers to build habitats or shielding. Others suggest studying the long-term effects of lunar exposure on plastics, glass, and metal to understand how future materials will degrade. Even the frozen waste bags could offer unexpected data: how microbes fare after decades in space, or whether Earth life could ever survive the lunar environment. Still, the larger point remains: we brought our mess with us. Just like on Earth's highest peaks and deepest oceans, we've left a footprint and a garbage trail behind on the moon. It's a reminder that space travel, for all its elegance and glory, is also a story of logistics, leftovers, and letting go. We think of the moon as pure and silent, but it's also the final resting place of broken tools, empty fuel cells, and astronaut poop bags, a museum of forgotten gear, a junkyard of progress. And it's still growing. With every new mission that touches down, the moon quietly inherits a little more of our presence and a little more of our trash. We all know the moon is tidally locked to Earth. It spins on its axis at the exact rate it orbits us, which is why we always see the same side. That familiar face has been gazing back at Earth for billions of years. But here's something that sounds like sci-fi, and kind of is if you're patient enough. One day, Earth might lock to the moon too. It's called mutual tidal locking, and it's a real, albeit distant, possibility. In this future scenario, not only would the moon always show the same face to us, but Earth would always show the same face to the moon. Imagine that one hemisphere of Earth locked in permanent lunar view, the other in endless lunar absence. Let's unpack how that could happen. First, understand the force behind all of this. Tidal friction. The moon's gravity pulls on Earth's oceans, creating bulges of water, our tides. But because Earth rotates faster than the moon orbits, we spin once every 24 hours. The moon orbits once every 27.3 days. Those tidal bulges are always just a little ahead of the moon in its orbit. That tiny offset creates a gravitational torque, pulling on the moon and giving it a slight forward nudge. This nudge transfers rotational energy from Earth to the moon. As a result, the moon slowly moves away currently at about 3.8 centimeters per year. Earth's rotation slows down. Our days are getting longer by about 1.7 milliseconds per century. This has been going on for billions of years. When the moon first formed, Earth spun much faster. A full day lasted only about 5 hours, and the moon was far closer. Over time, Earth's rotation has steadily decelerated, and the moon has spiraled outward. If this continues indefinitely, and there's no external disruption, we could eventually reach a point where one Earth day equals one lunar orbit. That's tidal locking. At that moment, Earth and moon would be in a 1-to-1 spin-orbit resonance. From the moon, Earth would stay fixed in the sky. From Earth, the moon would hang motionless over one part of the planet, always there, never setting. The rest of the planet? It would never see the moon again. But there's a catch. This would take billions of years, maybe tens of billions. Estimates vary, but some suggest it would take more than 50 billion years to reach mutual tidal locking, assuming nothing else changes. And that's a big assumption, because there are at least 3 big complications. The sun's as red giant phase long before we get to full Earth-Moon tidal locking. The sun will exhaust its hydrogen fuel and enter its red giant phase. In about 5 billion years, it will expand dramatically, likely swallowing Mercury, Venus, and possibly Earth. If Earth is consumed or roasted into a lifeless rock, the moon won't be around to lock to anything. Gravitational disruptions. The Earth-Moon system isn't isolated. Gravitational nudges from other planets, cosmic collisions, or future massive events could alter orbital trajectories. Over billions of years, small perturbations add up. Nothing is guaranteed. Tidal effects aren't constant. The rate of tidal slowing depends on Earth's ocean's atmosphere and internal structure. If sea levels change, continents shift, or the Earth's interior cools and solidifies, the rate of energy transfer could change drastically. Still, as a thought experiment, mutual tidal locking is fascinating. It's a reminder that nothing in space is static. Orbits decay, spins slow, distances change. Celestial bodies evolve over unimaginably long timescales, far beyond the scope of human lifespans or even civilizations. And what would a tidally locked Earth-Moon system actually be like? Well, if you lived on the side of Earth facing the moon, the view would be incredible. The moon would hang in the same spot in the sky every day, huge and bright, always full from your perspective. On the other side of Earth, total moonlessness. The tides would stabilize, weather patterns might shift, and Earth's rotation, once rapid and dynamic, would become a slow, synchronized waltz with its old companion. But don't pack your lunar-facing real estate just yet. We won't be around to see it. Earth will likely be gone, the sun a white dwarf, the moon possibly adrift. Still, the idea lingers. One day, in the quiet future of the cosmos, our planet might turn to the moon one final time, and then never turn away again. For thousands of years, we've stared up at the moon and imagined living there. Ancient myths spoke of moon gods and lunar travelers. Sci-fi writers envisioned bases, domes, and civilizations beyond Earth. And now, for the first time in history, those dreams are creeping toward reality. Because the moon isn't just a destination anymore. It's shaping up to be our first off-world colony. That's not an exaggeration. Right now, not in 50 years, but today's space agencies, private companies, and governments around the world are actively planning the first permanent human presence on the moon. And the reasons go far beyond symbolism. The moon is the closest and most practical stepping stone to living beyond. Earth is just 3 days away, a short hop compared to the months it takes to reach Mars. It has real terrain, real gravity, 1/6 of Earth's, and resources that we're only just beginning to understand. It's a laboratory, a testing ground, a survival challenge, and possibly a second home. Let's start with what's actually happening. NASA's Artemis program plans to land humans on the moon again, the first since Apollo 17 in 1972. And this time, the goal isn't just to plant the flag and leave. It's to stay. Artemis 3, tentatively scheduled for the late 2020s, will land near the lunar South Pole, where permanently shadowed craters contain billions of tons of frozen water ice. Water is everything in space. It's drinkable, breathable, broken into oxygen, and even usable as rocket fuel, hydrogen, and oxygen. If we can mine it, we can stay. NASA's long-term vision includes Gateway, a small modular space station orbiting the moon, and an Artemis base camp, a semi-permanent habitat on the surface. The idea is to establish infrastructure, landers, power stations, communication relays, and eventually research labs and crew quarters. But NASA isn't alone. China and Russia have announced plans for a joint international lunar research station, aiming to build facilities on the moon in the 2030s. SpaceX is developing its Starship rocket with the explicit goal of sending cargo and crew to the lunar surface and later to Mars. Private companies like Blue Origin, Astrobotic, Intuitive Machines, and ISpace are racing to deliver landers, rovers, and payloads, both for science and commercial exploration. This isn't science fiction. This is happening, and it's forcing us to ask a new question. What does it mean to colonize the moon? Unlike Earth, there's no atmosphere, no protection from radiation, no magnetic field. Temperatures swing from boiling to freezing within hours. So, any lunar colony would have to be incredibly resilient and self-sufficient. Structures may be buried underground, possibly in natural lava tubes for radiation. Shielding 3D printed, using lunar regolith, reducing the need to ship building materials from Earth, powered by solar panels placed on sunlit ridges near the poles, supported by robotic systems that can mine, transport, and maintain basic resources. Astronauts wouldn't be living in luxury condos, at least not at first. Think modular habitats, tight quarters, closed-loop life support systems. Every drop of water, every watt of energy, every breath of oxygen would be tracked, recycled, and rationed. It would be more like a submarine than a city. But the payoff would be historic. A functioning moon base would change everything. It would serve as a launch point for deep space missions. A lunar fueling station could slash the cost of reaching Mars or the asteroid belt, allow long-duration human research in low-gravity, critical for understanding how bodies and brains adapt to alien worlds, enable in situ resource utilization, building with what's already there instead of shipping from Earth, and provide an emergency backup, a way to preserve human life in case of catastrophe on Earth. It would also be the first true test of planetary settlement. How do we govern a place with no borders? Who owns what? What happens if people are born there, raised there, grow old there? At what point does a moon base stop being a research station and start being a civilization? Of course, there are risks. Radiation is a huge one. Without Earth's magnetic field, cosmic rays and solar flares are a constant danger. Any lunar habitat must have serious shielding. Micrometeorites, tiny space bullets traveling at tens of thousands of kilometers per hour, can punch through metal. Lunar dust is abrasive and clingy. And psychologically, the isolation, confinement, and monotony of lunar life could be just as deadly as any engineering failure. But we've faced worse. Colonizing the moon won't be fast, and it won't be easy. But the foundations are already being poured. With each new lander, rover, and mission, we're slowly turning the moon from a destination into a location, a place, with addresses, objectives, permanence. And someday, maybe not in our lifetime, maybe just beyond it, people may look up at the moon and say, that's home. Not all of it, not yet, but a piece of it, a foothold. We've been dreaming of lunar colonies for centuries. Now, we're building the real thing. To most people, the moon is still just a glowing disk in the sky, a poetic symbol, a distant dream. But for governments, space agencies, and corporations around the world, the moon has transformed into something far more strategic, a geopolitical high ground. Slowly but surely, it's becoming the front line of global space politics, a new domain where science, power, resources, and diplomacy are colliding. It's no longer just about going to the moon. It's about who goes, how they go, what they do there, and perhaps most critically, who gets there first. Let's rewind. During the Cold War, the space race was a two-player game. The US and the Soviet Union locked in ideological and technological combat. But while the Apollo program got Americans to the moon, no one followed. For half a century, the moon lay dormant, unvisited, untouched, politically irrelevant. That era is over. Now, the moon is once again in play. And this time, it's not just two players, it's dozens. The US, China, Russia, India, Japan, the European Union, South Korea, the UAE, Israel all are developing moon programs. And many are bringing in private companies, universities, and international partnerships. What once felt symbolic is now strategic. The reason? Several, actually. First, there's resources. We now know the moon contains valuable minerals, including rare earth elements, titanium and helium-3, a potential fuel for future nuclear fusion. There are billions of tons of water ice trapped in permanently shadowed craters, a resource that could support human life and power rocket fuel production. Whoever controls the moon's resources could hold a massive economic and logistical advantage in space. Second, there's positioning. The moon is the perfect staging ground for missions to Mars and beyond. Launching from the moon is far easier than launching from Earth because of the lower gravity. A nation that builds infrastructure on the moon, fuel depots, habitats, factories, could lead the next phase of interplanetary exploration. Third, there's influence. As more countries reach the moon, the opportunity to set the rules becomes part of the prize. And right now, those rules are unwritten, or at least unclear. That brings us to the Artemis Accords, introduced by the US in 2020. The Artemis Accords are a set of non-binding principles for peaceful exploration of the moon and beyond. They promote transparency, the sharing of scientific data, the preservation of heritage sites like Apollo landing zones, and the concept of safety zones, designated areas around lunar operations to avoid conflict. So far, over 40 countries have signed the accords, including allies across Europe, Asia, and the Americas. But key players Russia and China have not. Instead, they've proposed their own plan, the International Lunar Research Station, a cooperative moon base planned for the 2030s. It's a rival vision, rooted in a different geopolitical alignment, one that suggests the emergence of two parallel space blocks. Much like during the Cold War, this isn't outright hostility, not yet, but it's definitely posturing. China's space agency has made rapid advances, landing on the far side of the moon, bringing back samples and eyeing the lunar South Pole. Russia, though slowed by economic issues, remains a formidable space power. India landed Chandrayaan-3 near the South Pole, proving its capabilities. Meanwhile, private companies from the US and beyond are preparing commercial lunar landers, prospecting missions, and infrastructure projects. And here's the core issue. The Outer Space Treaty of 1967, the backbone of space law, explicitly forbids any nation from claiming sovereignty over the moon. You can't own land. You can't plant a flag and call it yours. But the treaty is vague on resource extraction, exclusive zones, and commercial rights. There's a huge legal gray area, and different countries interpret it differently. So, what happens when two landers aim for the same crater? What if one nation builds a permanent outpost next to an ice-rich shadow and another wants access? Who decides who stays or leaves? The answer isn't clear, which means the moon is quickly becoming not just a scientific objective, but a diplomatic chessboard. It's already visible in the rhetoric. Leaders are now talking about the moon in the language of strategy. National interests, strategic presence, space dominance. Agencies are developing lunar GPS systems, communication constellations, and even concepts for lunar internet and military surveillance. What began as science is veering towards space realpolitik, and just like on Earth, precedent matters. The first country to establish infrastructure, be it, and make it work, sets the tone. They define what's normal. They create the frameworks others are pressured to follow. In that sense, the moon is a test case for how humanity handles its next frontier. Will we cooperate, compete, coexist, or clash? Because, make no mistake, the moon is no longer just a rock. It's an arena for ambition, influence, innovation, and policy. And how we behave up there will shape how we handle Mars, asteroids, exoplanets, the entire future of space exploration. So yes, the moon is still beautiful, still ancient, still silent. But behind that silence, a very human drama is unfolding, one of flags, treaties, claims, and competition. The moon has become more than a mirror in the sky. It's become a mirror of us.